reason about it rather than running the code. So a lot of what we were talking about in terms of making code faster or making it correct, even better, is that you can look at the code, reason about it, and say, okay, these two things are equivalent or whatever it is. With non-standard evaluation, we'll look at some code today, you actually have to know that it's using a different computational model in that function. So you now have to manage two dialects or two actually very different languages that look very similar. That's the only reason I'm down on it, in the sense that it makes my life complicated. Certainly makes my life complicated because I can't read code anymore. Okay, because I have to know which dialect or which computational model it's using. And that actually has implications, as I showed you on Monday, that if I use something like code tools and the find globals function, it doesn't work. We went through a bunch of code on Monday about making something go faster, and we made it go 1,400 times faster. And I wrote it, by the way, that's all in a markdown file in there. So I tried to write a narrative. So rather than slides, you can actually read the whole thing, and rather than reading slides and try to figure out what I said that make the slides make more sense, there's hopefully like an actual text narrative, which is the way I like to do things. But one of the things I can't remember, I certainly did it, but I'm not sure if I put it in that narrative, is R has a compiler. Okay, so that actually makes the code go faster. Okay, so you can actually compile, if you install an R package, by default it will now actually compile that code. And that means the stuff I was talking about with the for loops, it actually will start looking and say, oh, remember I mentioned the for loop, it has to go find the functions each and every single time that are in the body of the for loop. Well, in an R package, we know that the search path is actually fixed. We know what other packages you depend on and import, specifically import, and therefore the compiler can do good things. The trouble is the compiler is for the R language. It ain't for another language. So if somebody writes code using tricks in R that allow it to behave differently, we can't compile it and you'll lose the speed. Okay, and also we do things like one of my grad students is working on stuff to make it parallel. Okay, so you just take serial code and then it'll automatically make the code parallel to run in parallel on multiple cores and do good things. Again, if it's non-standard evaluation, you give that up because we can't analyze that code because it actually has a different computational model. That's a drawback, okay? But other than that, the tidyverse is great. If it's more intuitive to you, that's great. The one other component of the tidyverse that is problematic is my experience is that people don't learn the basics on what I call the fundamentals of R, which is 99% or a little bit less than that, depending on what you do. You use a data frame, okay? And the tidyverse has the concept of a tibble, which is just a data frame, okay? The snag about it is that if you actually want to do something like somebody gave me code today, if you want to use a list, your brain has to actually change now because you're no longer using a data frame. So if you're using vectors, rather than data frames, if you're using lists rather than a data frame, you actually need another part of the language that you don't get to use very regularly. As a result, you have to switch your brain over into a different side. And remember, my philosophy, which is just my philosophy on this, is I want as few discontinuities as possible. I do not like to context switch, because then my brain has to start thinking about the wrong thing. If I have to, a good example of context switching is when I go from the train, where I'm typing on this, and I go into my office and I type on a keyboard, regular keyboard, my brain actually has to change, and it takes me a little bit of time to actually get used to things. So I don't like that, and likewise, I don't like moving between different languages, essentially. So they're the reasons the tidyverse isn't perfect. It certainly, it has a nice, one of the benefits is that it actually tries to make things consistent. There's no doubt that that's helpful, but that's tends to be the least of my worries. But then again, I have been doing this for a long time, so each to his own or her own, but be aware that you are potentially giving up some of the tools that are being developed by the compiler. There's a compiler in R, as I say, you tend to get a speed up of about 2 to 10, a factor of 2 to 10 by running that, depending on your problem. I've been working on a compiler where I'm getting speed ups of 300-400, okay, for certain types of problems. And there's no way we're going to compile out some of the non-standard evaluation because it's just, but maybe other people will, but it'll take longer. So therefore you might get held back. Yes? I can. It's whatever's not standard, okay, which doesn't really help. So how do you define non-standard evaluation? We touched on it, and again, I didn't really, let me just see, where am I going to find this? I have an example right here, okay? So let's take this, for example. Let's not take that one. Let me just go and do this one. Let's go over to this script that we looked at before. And we look down in here. And I think it was here. So this is an example of, where am I looking at now? So when R, so the way R works, and again, it's very simple the way R works. And that's what I like, okay? It's, you have a set of rules and you can reason about that small set of rules. When we look at something, let's just look at this one line here, okay? So this actually should get expanded out into the following, okay? So let me write it down, okay? So this actually gets, so the previous line, so I think I mentioned this a lot. This is equivalent to group by, okay, of tidy data. Okay, and then we have, what do we actually have? We have size, and what was it? Site size and depth. Site, size, and depth. And again, the tidyverse is not the only piece of code that does this. Built into the regular R in the, just with the LM function, it does exactly the same thing, except for it's a little smarter, okay? There's actually a more coherent model to this, okay? Is group by basically says, okay, when we see this, these guys, the way that R works, so if I do something like the following, plot of X comma Y, the way R works is very, very, very simple, okay? This, let me just quickly go on. When I do this in R, this turns into, this is just syntactic sugar for call this function, and there's a function with this name, with X and 1, okay? That's the same thing, okay? So why do I show this? Because that basically allows me to say that everything in R is a function call, okay? So 1 plus 2 is actually seen by R. After it just parses this text, it immediately turns it into that. Okay, so everything in R is a function call, okay, except for one thing, two things. That is not a function call, it's a literal, and this is not a call, it's the name of a variable, and we print the result, okay? After that, everything else has to be a function call. So now, that's a very simple rule. Yep. So if we have a literal value, so like 1 or ABC as a string, these are literals. So I'm more than happy to talk about this ad nauseum. Okay, but in another workshop I actually teach what I call the R fundamentals. And so what you actually have is we have this thing called a REPL, okay, a read eval print loop. That's what we have in Python and R, MATLAB, and so forth. It just sits there at the prompt, waits for you to type, and it reads. Then what it does is it actually parses, okay? It parses the text that you type. If it's wrong, if it doesn't make grammatical sense, it says there's a syntax error, okay? When it does make grammatical sense, then it tries to evaluate that code, and now it starts looking, okay? But in the parsing, we get some text like this as input, text like this as input. It parses this and turns it into a call like this. Okay, but in this case, this 1 is a literal value, and it just says we don't need to compute that later on. We already have the literal value now, so a string or the value true. And just because we're going to come across it later on today, that is a literal value. This is a variable name. Okay, they are not interchangeable. Okay, they just look like they are. Okay, and X here is also not a call, it's a variable name. So this is actually, if you were to parse this and look at it, it would have class name. Okay, so it's a symbol. Okay, and when we go to evaluate that, that says go find it. And now we're back to the function call. Okay, so we parse things, everything's a function call except for these literals and variable names. When we get a function call, we first of all say, let's go find plot. So we look along the search path or wherever is appropriate, and we can talk about scoping rules as to where this line of code will start looking for plot. Then it says, okay, fine. So while we're at it, I will just actually explain this because I think it's really helpful to understand how to think about R. So what actually happens is we find plot, and we know we're going to call plot, and we know we're going to call plot because it's got a parenthesis afterwards, so that's how it knows. You're going to call this with these two inputs. So what R does is it says, okay, I found plot. So where does it find plot? Well, let's go take a look. Where does it find plot? Hello. Oh boy. What is wrong with you? Okay. That's 1 second. Workshops. Again, if this, hopefully this is of, what is going on with my laptop? So this is, again, this is R. If you're used to RStudio, it's exactly the same thing except for the differences. Okay, so this is R. If I type search of this guy, okay, that's what I have. So if I now say, please find plot, the function plot for me, it says it's in the graphics package, which is down here. So let's take a look at what plot, the definition of plot is very, very, very simple. So R, when it's evaluating this, so it's read it, and now it's trying to evaluate this call. It first finds plot, and it literally opens what I'm going to describe as a box or a frame. This is a call frame. And this is important because when you actually want to debug R, you need to know about call frames. So this comes back to, okay? So then it says, well, here's the definition of plot. It takes X, so I'm going to change this to be A and B so it will be simpler. Okay, A and B. So X, X, okay, and it says Y, and it says dot, dot, dot. Where did those come from? They come from the definition of the function plot. Here's the definition. It takes one parameter named X, another parameter named Y, and it takes a third one, which is dot, 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 which is very special. Okay, so what this does, so we know we're talking about the plot function. We now have its definition. So R fills out a call frame, which is an environment, just like in the search path. It's a collection of variables that we look for things in. Okay, so it's just a container. It puts down X, Y, and dot, 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 and then it says, okay, but you're calling it with these two arguments. Let's go and match these arguments. So I'm going to actually do something like this. I'm going to say CEX is equal to 2. This is the character expansion size. We're controlling the size in plot. Okay, so this is a named argument. So R will say, I'm going to deal with the named arguments first. That's the definition over here. And this is a call. Okay, so they're different. Okay, that's the definition of the plot function. This is the call to the plot function. These are what I call parameters. These are what I call arguments. In R, we actually call them formal arguments and arguments. I like parameters and arguments just because I don't like formal arguments because it's too long. Okay, but that's fine. So what do? We match the named arguments first. This is the only named argument. We go through and say, do you match X? No. Do you match Y? No. Do you match dot, dot, dot? Yes, because dot, dot, dot consumes anything that isn't there. So we put CEX in here as 2 into a list in dot, dot, dot. Then it goes, okay, let's deal with the other named arguments. There aren't any. Okay. And then we'll say, okay, well, Now we'll match them by position. So therefore, this one must go to here, and this one must go to here. Okay? And if I'd written this as being plot of C, EX equals 2A, and Y equals, well, we'll do it, Y equals 10, and I put in another value, which is A here. Okay, so here's my call. Now it would match the two named arguments. CEX would go there, Y would go to there. The last remaining input is unnamed. It'll match X. And then R says, I've done all the matching. And by the way, if we don't match something, we fail. Okay, and I'm skipping one little minor detail. Okay, which is that we do partial matching as well, but that's not important for now. Okay, and life is good. Okay, all I've said actually is that we set X equal to A. That's a little fuzzy. That's not quite precise enough for my definition yet. Okay, what we literally do is we say X is equal to the expression or the call that will get me the value of A when I next need it. So let's suppose this was actually equal to A plus 1. What would actually happen is X would be equal to A plus 1, but it would not be evaluated at this point. We would wait until we first need X. Okay, so all we do is we just keep a connection to what the command was to get the value of this argument. Is that clear? Okay, so now we have these things lined up. We're ready to go. And now R says, okay, I've done all the matching. I haven't evaluated any of the inputs. That's a very weird thing in a programming language. It just says all of the inputs are just sitting, waiting to be evaluated when they're needed. So this is a thing called lazy evaluation. Okay, so so they're just sitting there poised. The definition of this function is very simple. It just calls a function named useMethod with one argument and one argument alone. Okay, so what does that do? Well, we're back to a function call again. If the function is called useMethod, so it starts searching for useMethod. Now it does not look in here. It does not look along the search path. It looks inside the graphics package for useMethod, and it doesn't find it. But remember when we were writing the package last Monday, we had an import statement for dplyr. We said, let's import dplyr because this package refers to some commands in dplyr. The graphics package also refers to, it imports other packages, including the base package, because they all do, and that's where useMethod is found. Okay, so we've got this call frame, and we also have the body of the function plot, which we're about to actually start evaluating. It's just a regular call, a sequence of calls. That's what the body is. Regular R things. We search along the function's own search path, its own special search path, not the user's search path. Okay, and we find useMethod. So lo and behold, life is good. We open up a new call frame for useMethod. So we look at that and we start doing the argument matching again. There's only one argument, it's unnamed. We match this to the first guy, and then we evaluate the useMethod body. Okay? And eventually that guy says, I would like X. And now we got to go and find, now we got to go and get the value that corresponds to X, which is the value of the expression or the language component called, which is A plus 1, and that gets us back to the very question we started, which is what's standard evaluation? I do remember the question. I do. Yes. So when you're writing packages, it instantly imports. You tell it to import. So you always have to. Sorry. You always have to tell it to install any. It always installs base. You never have to import base because you really can't go anywhere without base. Yeah. I have no concatenation function. I have no plus. I have nothing. I have no if statement. Okay. Everything in R, by the way, just remember I told you everything is a function call. This is also slightly surprising for most people when they actually, the if statement is a function. Okay. When we write a function that looks like this, we say function, and then we say 1 plus 2. It's a very boring function. Okay, that's fine. That is a function. The curly brace is not a part of the syntax. It's an actual function. You can do stupid things with the curly brace. You can make it behave. Have it send email. You know, okay, just it's like, that's not going to be very helpful. That's non-standard evaluation if you take that over, because now everyone looks at a curly brace and goes, I know what you mean, and you go, no, you don't. I fooled you. Okay, and that's because you can change almost everything about this language, which makes it extremely flexible and probably suicidal, because now you can't actually read this thing and actually understand what it's doing without running it. So yes, so you need base. So we just import base because you can't go anywhere, even include defining the functions. Okay, so this is so we've got these two call frames. Okay, you've got this guy, you've got the plot call, and you've got to call the use method. I'm going to quickly gloss over what use method does and how it does it. Why? Because it uses non-standard evaluation, exactly the thing I'm telling you don't do, but we have to for various reasons, but that's fine. But what it says is, what it actually does in this particular case is this actually ends up with a call to plot.default. Okay? So there'll be 3 calls. This is a call frame for plot.default. It says it's got X and Y and some other things. So it says, well, what's the value of X? And it goes back and it says it's this value of X, which is this guy. I still haven't used X yet. All I'm doing is matching the parameters and the arguments. So now, then this guy says, you know what? What's the length of X? Okay? And now now the plot.default function says, I actually want to know the length of X. And then we say, well, first of all, let's go find length. See, it's turtles all the way down. Okay, we find length, and we say, what's X in this case? Well, X is this value, which is back up here, which is back up here. And then it says, yes, now I need you to evaluate it. And then R says, I can do that. Remember, it's a function call. It's plus A and 1. So it goes and finds it plus. Oh God, this is amazing. Remember, I told you if you only need to learn one thing is how function calls are evaluated. So we end up with a call to plus, and we do this, and it says, okay, I need A. We say, what the heck is A? Well, we were up here at the prompt. Okay, we typed plot at the prompt. So now we go back to where this command, where A makes sense, which is at the prompt. And we say, can you find A, please? And we look in here, and we look in here, we look in here until we find A, and then that's it, that's A. Okay, makes sense. So if we don't find A in here, in this search path, it's over, it's an error. If we find it here, we stop immediately and put the value of A in. That is standard evaluation. Okay? Everyone with me? It's a long thing, partially because it's very recursive, because we kept on going. But it's actually, you get a function, you match the arguments to the parameters, then you actually start evaluating when we are looking for the name of a variable, that's this guy back over here, we look along the correct search path. Okay? For a function, it's its own little search path. When it's at the prompt, it's the user's search path. Okay, and now we can get into all of the scoping issues. Yes?
The functions we look at the group environment that first work with variables. Why is it a better idea not to pass variables onto the function and to rely on variables that are global variables?
Why is it good to rely on, or bad? Why is it bad to rely on global variables? Because when you send me your code, I don't have the same global variables. Then it can find it, yes. Why is it bad? Because I can't read it as well. And when I say me, anyone can't read it as well. It also means that it's actually a little less direct. Okay, we'll talk about this a little later on. So why are global variables bad? They're harder to read because you define it up here and then you use it down here, and there's no it's very easy to make a mistake and not actually have the right name and all that stuff. The other reason it's bad is because it's marginally less efficient. That's a really small concern. It actually has to, instead of it being available to the function directly, it basically now it has to go find it. So potentially so if you use a global variable that's in base, it has to search through all of these in turn, and people start attaching a lot of packages. That list gets very, 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 very long, and literally that sometimes happens where you have hundreds of packages. I can't remember. I think there's a limit that actually keeps it under 1,000 or something like that, because it's like, but unfortunately it actually happens. So that can slow things down. That again, that's an efficiency argument, but the real problem with global variables is, suppose I have, and this gets to writing functions, which we're going to talk about today, like good ways to write functions. That function is defined by that global variable. I can't change it. Whereas if I have a function that allows the caller to pass in the value, they can pass in the global variable, but they can also pass in another variable that is slightly different, that has more information in it or less information. So it's okay. Whereas if that just says, no, you have to actually, I'm only going to call that one variable, that function is more restricted. It has less flexibility in what it can do. And I'll show you how. So what I would actually do in this case, I would write a function that takes something like this, okay, and it basically says, okay, get my, which is global variable, okay. So this refers to a global variable, but I can override it anytime I want. So the caller can specify a different value, but doesn't have to, and that's much more flexible. Okay, so that's fine. Okay, so but the global variables come in because when we look for something in the function that isn't already defined, okay, in this case we were looking for the value of x, which is a plus 1, we had to go find a. And because a was an input to this, we started looking back where the call was made, which is at the top level prompt, and we start looking. Now, I switched nose. Now, watch this. So let's go back to this guy over here, which I said was the equivalent of this. Group by tidy data, site, size, and depth. This is non-standard evaluation. Okay? I issue this command. So I find this function, I create the call frame, I start matching these in. Where do I find site? I look in the place where this call was made, which is inside this function, so it should be inside this call frame. Okay? Where is it defined? It ain't. This group by function is not using the same rules to actually evaluate its arguments. And hence, I cannot understand what it's doing. So it could, it's not, okay, all the tidyverse is sane. It's just we can't reason about it, okay, in the same way. It could quite happily say, site, I'm going to find anything that starts with S. Okay, where? I don't know, anywhere I feel like it. Okay, what it does is it's going to find those inside tidy underscore data, or namely the first argument to group by. Okay, so this is basically going to say, first of all, look in here, and then if you don't find it in there, then use a different set of rules. Oh my. So what if I do this? That one typo is now going to give me totally different answers as opposed to an error. Okay? Okay, because it says I'm looking in here, I don't find it because it's using partial matching, maybe not, we don't know. We cannot reason about it until we actually look inside the code, and therefore you actually, in theory, you actually have to look inside every single function to see how it goes and evaluate its arguments. So that's non-standard evaluation, okay? And if you notice what we do here, we say lm of y tilde x on my data for fitting a linear model, okay? That's exactly the same thing, okay? except for there's a little trick to it, okay? It's basically saying this guy is special, okay? And it will look inside the data, but this here is a thing called a formula. And if I do the weird thing that does, okay, if we actually do this, and this, if you don't understand, by the way, what I'm talking about, please ask, okay? I guarantee you, if you think you're the only person who doesn't understand it, you are entirely wrong, okay? And if you think you do understand it, and you do, then you're the only person in the room who understands, okay? Okay, it's not very complicated, but it's very different and new, and it takes some thought and to actually think about the counterexamples. But where was I going with this? I was going y tilde x, okay? And I'm going to call this FM for formula, okay? And now I'm going to say, so what's the class of FM? And I'm now going to do the following. What's the environment of FM? It actually has a memory of where it was actually defined, okay? In this case, it was defined inside the global environment, which means if it says, I will look, if I know where to look for y and x, if I can't find them somewhere else. So what LM arranges to do is we will look inside the data, and then if we can't find them, then we actually trap the environment. And that's non-standard evaluation, but it's a very specific and well-documented and well-defined single approach to non-standard evaluation, which is through the environment of the formulas. And remember I told you this guy will look for it'll find the use method it's looking for by looking along its import. It's the same deal. Every function has an environment and it wanders along a sequence of environments, so we can reason about it, and formulas are identical, so you can reason about them in exactly the same way. So there is a consistency here that says, I know how to reason my way out of trouble. Unfortunately, this non-standard evaluation, which is made accessible by lazy evaluation, remember, because we don't evaluate site when it gets passed in. We only evaluate site when you ask for it, which means you can turn around and say, don't do it the way you would normally do it my way, okay? So, well, when you actually do that, it's non-standard, and we have problems, okay? By the way, when I do something like this, so what am I talking about? If I do something like plot of MT cars of 2. Don't make me a liar. Ugh. This is, I don't know what's going on. This thing has decided to get into very high resolution, and then I dropped it down to very low resolution. But so if you actually see what's going on here, you can't. But if you actually just draw this, the Y label is actually MT cars double square bracket 2. It knows what the command was. So I said plot MT cars, or plot of A plus 1. Now, we went off and got the value of A plus 1, which is a sequence of numbers, and it plotted those. But because of lazy evaluation, we could see the expression, the actual language object. And lo and behold, that's really useful, because we can start saying, hey, let's add it to the label on the plot. We can start looking and seeing what's going on and see how we were called. We get to see the value, but we also get to see what the expression was, which allows us to do really cool things. And it also allows us to do things that get us into trouble. That means you can't understand what something's going to work on. So that's a long answer to non-standard evaluation. Okay, hopefully it says that, first of all, we did actually get the benefit of that standard evaluation. Okay, and we can go through it again because it takes more than one time to actually understand standard evaluation. But non-standard evaluation is great. I sometimes use it for some things, but not for a lot of things, because you can't reason about it.
So the timer clearly, and you can tell that it's doing things in a different way because the syntax is so different from base R. But we install lots of different packages. How do you know when your package is doing things in a non-standard way and in a way that could get you? You can't. Okay.
You have to kind of really, unfortunately, this language is it's a great language. for fun. So people like me can sit at home and play games with the language, but that doesn't actually make it a good thing to do. You can drive a truck through this language. Now we just pray people use it sanely. And you don't. And again, in fact, actually, the tidyverse, I suspect, is not using any different syntax. It'd be great if it was using different syntax, because then you would clearly say that is just different. Okay, whereas what's actually happening here, so there's two pieces to it. That the piping operator looks like a totally different syntax, and it is, because of what I said it was doing last days. It's actually calling group by and inserting the left-hand side in as the first argument. But if it was the third argument, you'd have to put a dot in there, and clearly dot doesn't make sense, so you know it's a different syntax. But that's the piping operator, which is actually technically different from the tidyverse. Okay, so that's actually, these are two orthogonal elements. This is the tidyverse, and that syntactically is identical. You just don't know. And again, I'm not pointing fingers at the tidyverse alone. The LM function is also doing that sort of stuff in a saner way. There's one that is doing it in an entirely, there's one function, there's several. There's one function that there's one function that, again, there's one function on that screen that you've all used, okay, that uses non-standard evaluation, and it's using it right there, and it's using it right there on that screen. What is it? No, that's perfectly legit. Totally legit. That's a real function that behaves exactly the way all functions were made to behave, like that God intended. Okay. Okay. So there's a function here that you've all used okay. Function. That's you're getting close. That's it. But it's not that guy. It's Monday. Don't confuse me. I thought today was Thursday. So yeah, it's library, because let's look at library. It says library. I need to go find the value associated with the variable name dplyr, because that's what I just told you it happens. It says that's a variable name, so therefore it doesn't evaluate dplyr until until we've matched the argument to the parameters in the library call. Then if somebody refers to that guy, and by the way, this is a very useful thing to be able to do when you're writing functions. So I'm telling you this because you can get yourself into all sorts of fun and games. See, so we would create a new call frame with an argument, with a parameter name package, and another one called pause, and so forth. Then we start matching the arguments to the parameters. There's only one argument, which is dplyr. That's a variable name. But this function is a stupid function that has another function defined inside it, which is really, really annoying. And there you go. This is the magic that makes this happen. It says, I'm going to substitute the value of package with itself, which gives me back the call. Okay, so it would give me back the a+1, not the value of a+1, just the expression a+1. That's how I can throw it onto the axis labels. Okay, in a plot, it also basically says, okay, library, you're special because you users will not put quotes around this to say library of the name dplyr. I'll let you do this. And as a result, it's non-standard evaluation. Nobody gets hurt. Okay, that's fine. We get hurt when we get the wrong answer. You don't get the wrong answer here. You get an error when you screw up here, and you rarely are. This is rarely a problem. But non-standard evaluation can give you the wrong answer. Why? Because, as I say, if you type cite here, and you drop the E, you will get a different answer. And if you have something called sit, you will get, hopefully, an error. The worst that can happen is you don't get an error. And now you just get nonsense, and you start publishing papers that say, up is down, and okay, or something that seems reasonable is significant, but it ain't. Okay, and we're in bad news. Okay, so that's That's why non-standard evaluation is problematic. The tidyverse is one of the things about the one other aspect of the tidyverse, which is another thing, again, going back to you. I remember what I said was I hope that you guys will actually think about writing packages for your own use, and then gradually they will grow into use for other people in your lab or whatever, and then to other people in your discipline, and hopefully you will get rewarded for that, for writing software, and that's a good thing. The other but when you do that, there's a whole workflow, and there's a whole set of conventions, good and bad, and that is you don't go around changing your function names just for fun. Today, so Tuesday, my function is called Bob. The next on Wednesday, it's called Jane. Guess the name tomorrow. Okay, or it takes 3 arguments, and now it takes 4 arguments, and by the way, the first argument used to be the data frame, and now the first argument is some other silly thing that doesn't seem to be first. And unfortunately, sometimes, so the tidyverse has changed over time, so therefore your code now breaks. Okay, so if you have an old version, so we like stability as well. But our core team takes the other extreme, which is nothing will ever change. Okay, which is, it means your code doesn't break, but yeah. Okay. Okay, everyone happy? Yes.
Quick question about how formula in LM would work. How would that work for like multiple arguments?
How do you mean multiple arguments?
Well,
okay.
So you sure that a generic formula applies.
Yep.
Can you just write how that would work with the example code? Because I'm not quite clear on.
So I'm trying to figure out which example code. Sorry,
Group by.
Well, it's a totally different. I mean, I'm just trying to figure out exactly what you're asking. Okay, so I'm happy to try to figure out. LM says, you got. There's a beautiful little problem here with LM. So I mean, if we talk about with LM, so well, sorry. Okay, is your question this? Okay, I can go backwards and forwards. This is group by tidy data, site, size. It's going to look for all of these. Okay, it's going to look for all of those in exactly the same way by looking inside here. So it just goes through them one at a time. And let's take a look at the group by function. Okay. There we go. Now this is another part that's fun too. Okay, so let's just do, now we have fun, which I don't want to get into quite yet. So now we can't actually see this, and this is another oddity. This is, okay. So what does this guy, see the add equals false here, okay, in the group by, okay? So let's just take this example here, okay? So we say group by, and again, we could use the pipe or not, okay, but I'm just going to say, group by in MT cars, okay, so that's the data set, okay, and now I say something like MPG, okay, and weight, okay, for those of you who don't know, and there's no reason why you should know, but this is part of the issue is, these are the columns in the MT cars data set, data frame, so therefore these guys are perfectly fine, okay, they will get found, okay. But now, what happens when I do this? Add equals X. Where will X be found? X is a value that says true, true or false, let's say. Where will X be found? No, because we're passing it in, so it can never find it in there. It has to actually find it. Well, it can find it in the parameters, but it will search at the prompt. Like remember I said we're looking for A+1, so it'll find it here. Well, then why doesn't it find MPG the same way? You don't know how that's going to get found. That's part of my issue. That will get found differently than this guy, than those two guys. So so literally 2 different arguments in the same call will behave differently. That's your multiple arguments. So it'll handle MPG and weight without any difficulty. Why is that going to be the case? Because when we go back up and look at the definition of this, It's still sitting there. There we go. So it says .data. That will get matched to empty cars, okay? Remember, what's going to actually happen is we're going to get, and by the way, here's just one other important gotcha that makes life entertaining until somebody tells you why it's so annoying, okay? Remember what I said? We're looking for group, we're going to call group by, so we open a call frame. We look at the definition of group by. We have a parameter named .data. We have another one called .dot. We have another one called add. Then we match the arguments in the call to the call stack, or to the call frame. So we start with the named argument. This is the only named argument, and it matches exactly add. So this X gets put into the value of add in the call frame. Then we go on to the other ones, which are unnamed, so this gets matched to .data. And then this was the next one available, gets put into ., and WT gets put into ... Life is great. Okay, now we're all ready to go and life is fine. Now, imagine I, in my wisdom, because I'm allowed to do this, I could say something like this, dash, because I'm lazy. Okay? That's a named argument. It will match that guy. What actually happens is this one will match first because it matches exactly. Then this one does not match exactly, so but it does partially match, and uniquely and unambiguously it matches. So this guy gets mapped to that, and we go ahead and we match the same thing. So the logical argument would be that therefore nothing matches exactly. Round 2, let's do partial matching. That one partially matches. This one, does it partially match anything? Yes, but it's after ... so it doesn't. Oh, that's going to get you. Oh, that's going to get you. Okay, that's going to be very, very annoying. So if I actually do this, okay, so no, I didn't actually, okay. No binding for X is one error because I have that. Okay, and this will give me the same error. So if I put in X equals 10, okay, and I match it up this way, okay, this behaves itself. I do not know what it did. I actually have no idea what it did. I don't know whether it found X inside. Well, I couldn't have. So it must have actually behaved differently for these two than it did for X, because there is no X inside the empty cars. So literally within the same function call, though, the way these get evaluated and the way these get evaluated is different. Everyone happy? Anyone happy? So, you know, but honest, there's one other thing I mentioned about the tidyverse on Monday. And again, I'm not here to actually knock the tidyverse. A lot of people are using it very productively. Go ahead. Remember what I said on Monday was that I want you to aspire to write good software, and not just software for other people to use and become a professional software developer, but actually software that you can rely on, that you can reason about, and actually when you get to your dissertation and you're using some code, that when we grill you in your exit exam, okay, that you can actually justify it. If you're proving math or if you're doing something else, you should be able to show that it's correct. And if nobody can do that, that's not good. The trouble with the tidyverse is great when we're doing interactive coding at the prompt. When you lift that same code and put it into a function in a package, it's not. Hadley will say it doesn't work that way. So that's the discontinuity of. Oh look, I can start programmatically automating a lot of things, and all of a sudden the same code behaves differently. Okay, because it's inside a package. Okay, but by the way, another example, which is there's a function called this, which is very nice. Okay, we do something like MPG plus cylinder, which is goofy. This has been around in R, and the person who put it into R should have been shot for that. Okay, which is it makes life simple because we don't have to say MT cars $MPG, MT cars $SIL. Okay, so it just cuts down on typing, and it makes this code reusable because I just have to change it in one place. And again, we don't like repeating ourselves, but unfortunately this uses non-standard evaluation. Okay, it's exactly the same as LM, except for it doesn't use formulas. It's exactly the same as the group by. It's there. Not all things are good ideas. Okay, everyone happy? Any other questions? Everyone's worried. God, if it takes that long to answer one question. No, it's these are. I hope we went through a lot of other stuff. I have a question for you. So remember the where is that window? Remember this is the URL for I think this is the URL for the Git repository. Okay, you can go to that URL, or you can git clone this this repository. Hopefully there is this, which I believe is up to date. There is a new directory there since Monday, and it was volunteered to me yesterday evening. Thank you very much. So let's take a quick look at this. And by the way, just let me say one thing. You don't write code that looks like this. This is for pedagogical purposes alone. Okay, okay. This is funds. You know, we started at fund 0, then 0.5, then 1, then 2, then 3, and so forth. These are versions as I go gradually, as I refine the code to make it easier for me to understand or whatever it is. You would, I hope, git commit each version of these so you can go backwards in time rather than actually having all of these. Some people get confused and say, okay, this is the best practice. Let's write code like this. Oh, no. Don't have lots of the same function lying all over the place. And this is the original code. This is beautiful because this is a simulation. So there's no data that we need, which is great, because I got this mail and I was just about to say, you didn't send me the data after all, but I was like, okay, this is good. Okay, so after all that I said on Monday, and then, this is good, okay? By the way, just as a thing, I look at this and I go, beeper? Do I really need it to beep at me when I'm doing this? No, I do not. So why do I have to install this package, which installs 2 other packages? It doesn't matter. It's a very small point, but it is nice to actually have the world's smallest example so it reduces the hassle. This is great. We have a function which we define here to actually define two values, which is good. This is overkill. You could have just defined the 2 values here in one go with these computations, but this gets to reusable code. It's amazing how, if a lot of people have the attitude, which is, I'm only going to run this code once, okay, and then I want to use it for something slightly different. So this is actually doing a simulation and it does actually lock these values of alpha and beta in. I have a very vague idea of what this code does. I looked at it yesterday evening. I don't need to know what it does. Michaela will tell us as we go along. But when I misunderstood, but we go along. But we got these 2 values, and actually it turns out that we have a function up here. And again, by the way, thank you so much for giving me this code. I really appreciate it. I'm not making any judgments, I'm literally going to see if I can actually make it easier for me to understand, and then to make it reusable, okay, and flexible. Okay, make it more flexible. I ran out of time because I had to go to meetings this morning. But we'll do it ad hoc. Yeah, so we'll do it informally instead of live to make it even more extensible at the end, and then I'll commit that code later on. This is the code. Okay, it's a for loop. No problem with the for loop, except a few. Okay, because it makes more work for me. Okay. It's a for loop that goes between 2 and 24. Okay, by the way, whenever I see numbers hard-coded, it makes me anxious, because it means that I don't know where those numbers came from. They don't have any symbolic meaning. Okay, I'm guessing the 24 is 1 less than 25, and 25 is the magic rule for the central limit theorem to apply. Does that have anything to do with this? No. Oh, so close. I was going but it was a rich interpretation. It was like, okay, let's go. Okay, which is perfect. There's a very silly rule of thumb that says the central limit theorem applies when you get to 25. Okay, we love that, but it's wrong. But no, yeah, but no. So I was hoping 25 would be the magic. Anyway, but these are sample sizes, and we draw. Okay, and this is good. So again, this print statement that says I'm still alive. It may be taking hours for me to get to the next round. So you have no idea. So putting in prints, again, it would be nice, as we saw the last time, to say, make this an option so it prints, so that somebody can control whether it prints, like if verbose, print I, or print every 10th one, or whatever it is. And then we have another loop, so nested loops, always fun. This makes R sort of cry for a while, okay? But this is I really can't say this enough. This code is perfect because it runs. I don't want good code that doesn't run, or good code that does the wrong thing, or good code that we don't understand if it's doing the right thing. Get it working, and then it's easy to fix. Okay, so it creates a data frame by calling matrix, by generating an R beta. So it generates I, which is this guy here, the sample size. It generates, so essentially for each observation, it generates 16 values, sticks them in a row, and then it makes I rows of this thing. So these are the parameters of the beta distribution. Okay, so that's fine. So it makes a matrix, then creates a data frame. Then it stores them into this thing. It stores this one instance into this sim to data save one. Okay. The good news about this is it's never used again, so that's good. Okay, just like might as well put it somewhere that will somebody's going to have to clean up. Okay, so but this does lock it down. So if these data were to get big, we would be saving stuff that we don't need. Okay, but that's okay. So the good news is, so I always say this. I mean, when you get to write your thesis, you don't actually sort of say, oh, by the way, here's a chapter that has nothing to do with my thesis, but I thought you might be interested anyway. Okay, so I'm going to read this code, so therefore, if we can make it as small as possible so that there's no extraneous stuff, that's good. So this is extraneous, but I don't know that until I actually read the whole code. So let's edit that. Then what we do is we basically go compute for each of these rows. So I tell you, I have to think about this. I was going like, oh, which one is, and as you said in your mail, this is a collection of lists, because you got a nested loop, you got lists within lists. And then my brain, I was like, oh, what's actually going on? So where did I put that thing? There it is. So what are we actually looking at here? I believe what we have is, so we have I rows, 16 columns. Okay, then we sweep across here and we compute the mean of that row. And we also then compute the SD. Okay, and bingo, we do this. And we do this 1,000 times. Okay, and then we move on to the next I, which is, so I is now 3, and we do this again. Okay, so we compute this, then we get, so we will end up with a vector of means and a vector of standard deviations of length I, but there's 1,000 of them. So this is a fun one. Okay. Then we move on after this, after it beeps. Okay. It's really helpful, actually. I fully understand. It's like this is sitting there for a long time and it beeps. Oh, good. Okay. Totally with you here. Totally with you. Okay. The other people have a tweet. Literally, it tweets and tweets them. So you go, okay, time to go back to work. Okay. Beeping is just as good. Okay. So this is good. So then we go on to step 2, which is to actually, and we can talk about this, but then we're actually going to analyze the results of this and do t-tests on the results. Okay? Now, how are we going to change this? I'll take any and all suggestions. This is where you get to do the work. And you can out loud read anything I wrote. Anything you want. I mean, you should keep it so that the thing does the same calculations. You can make it simpler. One goal would be to make it simpler. Another goal would be to make it more general. And another goal would be to make it faster. And I believe all those goals are actually, they are satisfied by some changes. The same changes, which is actually nice, as they're not competing goals. Yeah. That's what I meant by simpler. That was what I meant by simpler, more flexible, and yeah. So the lists are a slight problem. We have to allocate the lists up here. By the way, if you remember, and again, it's not a big deal because these are small numbers, but in terms of efficiency, and again, if I'm going to be running this for different R beta and different distributions, larger samples, larger numbers, larger than 1,000. If I'm going to be beating on this heavily, I may be concerned about making this efficient, in which case I want to pre-allocate these lists to have the right length because we're concatenating them all the time, okay? So that's a problem. And it may, and again, it may be that this is not a big deal because the numbers are small, but if we're concatenating, okay, but there are times when we may have small numbers, but we're concatenating really big things a few times, and that could be a problem. We'd still be better off pre-allocating like I talked about on Monday, okay? So my argument is I don't like for loops because you have to do this, then the for loop, and in the for loop, you've got to actually arrange to put things into the right place, and that means my brain hurts, okay, because I actually have to think about it. So in this case, I'm going to show you just to get the swing of things. When I started working on this, I go like, and again, I am not holding myself up as a model for that you should do things my way. You really shouldn't. My brain is very bizarre, okay, and I getting increasingly more distractible. So like I'll just do, and I'll venture off and do other things. But I think the right thing to do is let's focus on this, then let's focus on step 2. They are connected because if you change the data structures, the format of the results up here, you're going to have to change down here. But that's okay. We'll still work sequentially. So I'm now looking at this to show you another point. Okay, so that's the only reason I'm jumping down to route 2. So what we actually end up with as a result of what you end up with in here, just before the beep, you end up with this thing. We end up with I have this 2 through 24. So you end up with a list with 23 elements, and each one of those elements is, and this was slightly, this is fun for me. I'm going to ask you all a question, and you're going to, I did not know what the function would do, but what you end up with is, you end up with a list of 23 items. I is equal to 2 up to 24, 23 items. This element here it's got, what has it got? Well, remember I told you it had means and standard deviations. It is, as far as I recall, and I can check, it's got 2 rows and it's got 2,000 columns, correct? And it's a data frame because it says, make me a data frame. Out of sim data service summaries, when sim data save summary is this guy, which is the data frame here, we get 1,000 of them, okay? If I'd asked you, if I told you that this guy here is got 1,000 elements as a list, and each element is a data frame with, which has got I components, I believe. Is that right? Did we get 2 here? Is that 2? Is 2 the right number? I have to check. Maybe it may happen to be coincidental. I think it's 3. It's I. It's I, isn't it? We get I rows here. That's what we get. Thank you. Thank you. 2 is for the first one. Okay. Okay. Thank you. Okay. So this is fine. So what we actually end up with, we end up with a list. So this is the outer list. By the way, if you're getting confused, that's exactly the point. It's when you have lists of lists, you go like, oh, my brain is about to explode. I'm one level higher up than I think I am. So let's try to avoid lists. Okay, but basically what we get, and we can run this code, it's pretty fast. When we get down to here, when we finish this for loop, we end up with a list with 1,000 elements. Each element has as a data frame with just 2 columns with I rows. And when you do this thing on a list with 1,000 elements with 2 rows, 2 columns and I rows, what do you end up with? I don't know. I do now. Is not what I would have expected. It could either stack them on top of each other or it can concatenate them sideways. And it chooses to do them sideways. Okay, so it grows out to be a 2,000 column I row data frame, which is okay, but it may not be what we want because they are actually, in this particular case, all the same. They're all means. So you could actually stack them all on top of each other, and that might actually make more sense. Anyway, we end up with a huge, wide 2,000 column. So the first column is the mean, The next column is the standard deviation. The next column is the mean. The next column is standard deviation. We're only interested in the means, so we skip over every second one. Don't laugh. Oh, you've all done this. You've all done this. Oh, you. Oh no, the TA.
I take no responsibility.
This is.
He's taking initiative.
Honestly, I could. Everyone's been here. I mean, there's no. As I told you, my boss, who was a fellow of Bell Labs, which is a very prestigious thing in Bell Labs and other places, and she said, "I'm not showing you my code. I'm embarrassed." Like everyone has code. I have hideous code lying around the place. You know, this is not hideous. This works. It's just, but what it is can we learn from this to actually, can we reason about, can we make it more succinct? Can we make it easier to write? And it takes practice to write things straight off. But we do actually have to skip every second column, which is perfectly fine. So this is just like, oh my God, this is a lot of work. That is not, so I'll show you what we've done. What I did with this, just pray it gives me the same answers. That's another trick, is like you actually have to get the same answers. Now, good to say, look, my code is much shorter. Doesn't do what you do, but that doesn't matter. You know, we actually have to make, but if we can get it to be shorter and simpler and more flexible, then it's a win-win-win. So that's what we get. Okay, I've given you all long enough. Tell me some things we could fix here to make this simpler and less lists. Yeah, so that one, yeah, so let's just kill that one off. Okay, that's dead because it's never used again, so we just kill it. So that was the easy one. It's like, but a good one. Okay, so that's never used again. And at some point it might, in fact, actually, you kind of know that it better not be used again below here. Okay, why? Because it's inside this loop, and the next time you get round to the outer loop, the I loop, it's going to overwrite the same ones. So this is annoying because I wrote a version of this and I said, I want to check to see do I get the same answer. So let me run it on the short and simple one for 2 and let me compare the results for these. But hang on a second, I only had the ones for 24. So it's like, oh, I'm comparing the wrong things, and it distracted me because I started comparing them, go like, why aren't they the same? Oh, it's because these guys were only being collected within this, you know, that they, only the last I was getting collected. So it's only for 24. So you have to reason about this. Okay, anyway, so that's fine. So that's gone by the wayside. Anybody else? Let's do some simple fixes to make this. Let's start removing some letters. Yes. It's a very good approach. So we've got a slight difficulty. So that's a very good approach, except for, and we could go that way, okay? And what I've done, again, for pedagogical purposes, so that is entirely the right way to go, is you say, what do I want to get out for the next stage, or for just so I can make a plot or whatever it is. Then what are the inputs I need? And let's write a function that takes those inputs and maybe a few more to give me more control and more flexibility. And let's aim towards figuring out in as few steps as possible how to get the output I want. And ideally, what I would do, and we can talk, I'm not going to do it quite here, but we'll talk about it maybe later on, and definitely on Friday. We'll also sort of say, and how can I actually start saying that thing I want to do is made up of 3 smaller but still high-level concepts, and I will make functions for each of those, and I will go all the way down. Rather than making one huge big function, I will write lots of little helper functions, and then my top function will only have 3 lines of code, okay? Or as people look at my code, they go, it has 3 arguments with default values, and they just return the value of one of the arguments, because everything gets done in the function, in the default values of the arguments. I said, so that's a good way of going, but I'm going to change the game here a little bit. Is let's actually say this is what we want at the end, okay? We're going to talk about this too. Let's end up with this data structure. So that just for the immediately, let's focus on two things. First of all, I mentioned this earlier, I mentioned it. Nobody believes me, okay? But it does come back to bite you once, and after 3 days of figuring out why it bit you, you'll never ever do it again. But I'm going to try to save you all 2-3 days of misery, of misunderstanding something. Before we start removing characters or letters on this board, okay, on this thing, let's add 8. Let's add 6 letters that will make this code better, more robust. And I'll give you a hint. It's 3 letters twice. So that's even, I'm narrowing it down. Come on, you can all throw out random 3-letter. Okay, I'll even tell you this. They're all uppercase. And I alluded to it earlier on today. It's on the board. T? That's not 3 letters. No, they get TTT. I need those to be true, okay? Because this, remember, true is a constant. It's a literal value, and if I try to change it, R says you're not allowed to do that. Capital T is for the t-test, okay? It's for time, and we often say time is equal to 0. Now, if time is 0 at a starting point, that means time is t equals 0, which means t is false, because false is 0. So t can take the unfortunate value of 0, and all your logical conditions will be wrong. Okay, it will be exactly backwards. So this would say t, if by chance somebody has t equals 0, this would say that t, do I remove the missing values? No. Of course, I meant yes. So true is a better thing. I hope you never find anyone who got caught by that, but if they did, that's the last thing they looked for. Okay? And it's really annoying. Yep. If I do, pardon? So that's the other thing, is this actually is not going to happen. Although I could get something close to it. I won't get missing values. You can't, so by the way, just for those who aren't familiar with the beta distribution is a probability density function for a random variable, takes values between 0 and 1 or whatever it is, okay, and so forth. R beta is the way of generating random numbers for a beta. So there's R norm, R exp, R pos, and all these different things. This will generate values. These are vectorized functions, which means that you can use them very cleverly to actually do one call and generate values from different distributions, with different parameters. In other words, from the beta distribution, life is good, but you won't get missing values. But what happens if I said that the shape was actually -1? What would I get? I'd get a not a missing value, but something very close to it. I'd get a nan, which is not a missing value. Missing values are, I don't know what it was, but it's a real value, but we just don't know what it is. As opposed to a nan is not a number, because it just doesn't make sense. It's not the parameter -1 here is not a legitimate value for this distribution. So rather than throwing an error, it gives back NAs, and but an NA is not, a nan is not, an NA is not a nan, so this doesn't apply to that. But if I was writing this as a function for other people to use, I should actually say, I should check to see are alpha and beta actually legitimate values. Okay, and say, I'm sorry, alpha is fine, but beta is negative. You're an idiot. Okay, or maybe something slightly more polite, or maybe some ways even to actually suggest ways to correct this to the user. Again, going back to the cryptic error messages that you read and you go, I have no idea what this means. Well, if you're writing it, you should write it so that the person knows what it means. So we should put in some checks. If I was to turn this into a function, that would be fine. Again, that wasn't the purpose of for writing this, but we might as well turn this in. Okay, so we should put RUE here, or else we should get rid of the na.rm. It doesn't hurt us here at all, but it's just not going to. It's superfluous because we're in control here. Now, what I would like to know, though, is if I'm thinking about this, and I'm encouraging, and you might sort of say, "Oh, Duncan, I've got much better things to do with my time than this," and you're right. But you should think about maybe I could make this. I'm doing a lot of work here, and why the R beta distribution? Why shouldn't I be able to use the exponential distribution? Okay, so let's make this more flexible. Well, then why can't I actually use real data and actually use an empirical distribution, in which case there might be missing values in there, in which case, okay, so I would sample from an empirical distribution, in which case then this would become an issue. So do I want to, if I'm starting to think about making this more general, then I probably want to start thinking about adding these extra things, especially if I've thought about them before. I don't want to remove them and forget about them. Okay, so, but it's quite easy to see how you might actually make this more flexible. In fact, hey, while we're making this flexible, I should be able to change the sampling distribution. I should be able to change alpha and beta. I should also be able to change the statistics because I like looking at maximum and minima, okay, of things because they're really hard to estimate well. So let's look at the sampling distribution of those or the t-tests for those. Okay, so maybe I want to change that too. So we can start thinking, oh my God, let's start changing the entire thing. Okay, and making it so complicated, but so flexible that no one will ever use it whatsoever. Okay, so there's a point at which we go, okay, enough. Okay, you had your hand up, sorry. No, somebody had a hand. You did, thank you. Because then you wouldn't be able to skip it later on. And where would the fun in that be? 1 second, sorry. I'm back. Sorry, I'm just getting thirsty. The answer is yes. This is exactly the point you were making. Is like, what do we need at the end? Well, then why are we doing extra calculations? Sometimes we do extra calculations. Sometimes we only get to see a small part of the bigger puzzle. So we're computing the SD for a reason, which doesn't concern us at this point. But that's one way we could change it, is not compute the SD. But the nice thing about this is, give us a great opportunity to actually say, how would we go about doing this? How would we fix it? So let's just leave this code exactly the way it is, but let's just focus in on here and let's just make it a little bit more efficient, simpler, and so forth. Do we need the data frame and the matrix? Question? Anyone? Well, yeah, well, do we need data frame and matrix? Probably not. We can get rid of one of them. Okay, but we better be careful how we get which one we do. It's not that we don't need the data frame. What's actually happening here is matrix will give it the nice row column structure, the I rows and the 16 columns. Matrix then turns it into a data frame. The data frame then we have the structure, we turn it into a data frame. And then the magic happens is we call apply. And what does apply do? And let me just, somebody asked me about this. This always causes confusion for people who aren't familiar with R. So, and I was asked explicitly about this. So what does apply do? And one of the nice things about this example is it allows me to show things that people seem to not be aware of about apply, the apply family. Apply, okay, of my table, of my two-dimensional structure. In this case, I say in the dimension 1, which means go row-wise, and then I say, and I give it a function, some fun, and what it does is it goes through and it takes out that first row, because we said row, and it passes that vector to the function. So this function is written something like the following x, it just gets the vector x and it does something, it computes the mean. So we're going to give it 16 values and it's going to compute the mean. Okay, that's fine. Okay, so that's what the apply function does. It says take this and repeatedly apply or call this function to different units. In this case, we're saying row by row by row by row by row. If we'd said 2 here, it would be column by column by column by column. And if we do lapply, well, that's different. Okay, and if we do S apply, well, that's the same as L apply, except for it's different. Okay. No, it's the same as L apply, except for it does something at the very end, which it literally calls L apply and then says, can I simplify? That's what the S stands for, and S applies, can I simplify the result? And then there's V apply, which says, yeah, you can try to simplify it, but you're going to get it wrong. So I'm going to tell you what the heck you should be doing. I'm going to tell you that you can simplify it, but I want you to do it this particular way. I'm going to tell you the type of the result of each of the individual function calls so that you can create a vector. Okay, that's the vector apply. The L apply basically says, I have a list of things, and I give it a function. Okay, give it a function. This just says, instead of, I needed a 1 here to go row by row by row, or 2 for column by column. This is just apply with nothing in front of it. The L apply says, well, you got a list. This is an ordered collection of things. It's pretty obvious which order I should go in. This one, then this one, then this one, then this one. And what I should do is I should give you back an answer, which is, I should be careful here. Let me just, where did I put that thing? No idea. Okay. Oh, there it is. Okay. It's upside down. So this is what it does. Okay. So we have a list. L apply, and okay, we have a list, and we give it a function. Okay. And what the result will be another list. Okay. That's where the L comes from. Is the result will be a list, and it will have exactly the same number of elements. And this one here will be f of x square bracket 1. Okay, and this one over here will be f of x square bracket 2. Okay, and so forth. So that's all we're doing. It just goes through them. And it does a loop for us, and it allocates the answer for us, and it pre-allocates it so it doesn't have to concatenate, and it just does the right thing. So in terms of a for loop, it's actually simpler to use than a for loop because we don't have to declare a variable and then expand the variable, and we don't have to shove the answer into the right place, okay? Because that's just hard work, okay? It's especially hard work when you get down to here, where you basically are saying, oh, let's skip over every column. Now, where should I put the answer? I should put it into wherever I currently am as I'm moving along the columns, divided by 2. But I have to add 1 because I'm off by, oh, good God, off by 1 arguments are just the bane of my life, okay? So this is hard work here, okay? So you literally, whereas if we could get an apply to do this, we wouldn't have to worry about anything going on. And I can do that very easily here. Instead of skipping over things, I just tell it only to work on a few of them. I tell it which ones to work on, and then it fits into the apply model extremely quickly, okay? So apply is for matrices. Is that true? Anyone want to quibble? Go on, somebody quibble with me, okay? L apply is for lists. No, L apply is for ordered collections of things, and L apply will return a list. S apply is for an ordered collection of things, but will try to simplify the result of L apply. V apply is for returning a vector, okay, but it still works on an ordered collection. What's an ordered collection? R has very few data types. It has no such thing as a scalar. There's no such thing as a single number in R. It's a vector with only 1 element. Okay, unlike all other programming languages, which have a scalar and a vector or an array, R only has. We deal with data. You guys may have small data sets with only two objects, but we still have 2. Okay, you can't take the standard deviation of 1. Okay, so we work on multiple things, and this really influences the spirit of the language that we're working on samples and subsamples, and we're doing everything to the observations the same way, and that's what we're doing here. So what we have in R is we have a logical vector, an integer vector, a character vector, a numeric vector, complex vectors, but don't worry about them, okay? These are ordered collections, and then we end up with a list, which is an ordered collection of arbitrary things. Logicals all have to be logical. When you combine a logical with a number, then the logical turns into a number because they have to always get, I wrote these in order here. So Combining a logical with an integer means the true has to become 1, the false has to become 0. Combine it with the number 1.5, they all have to become decimal places because that's why we don't lose information. Combine them with characters, they all have to become characters because that way we don't lose information. Lists are nice. You can have a list with 2 elements. We don't care what the types are. It's a generic, each element can be anything. Where do matrices fit into this? And where do data frames fit into this? Okay, a data frame is, if you care, and again, hopefully you all know this, but if you type of MT cars, okay, and if you type class of MT cars, you'll get 2 different results. This will tell you that it's a data frame. This will tell you it's a list. The fact a data frame is built by using a list. It's a 2-dimensional structure, okay, but it's really a list, which is a 1-dimensional structure. The great thing about a data frame is each column sits like this. So the elements of the list are the individual columns, but they all have exactly the same number of elements in them, or else it can't be a data frame. So it's essentially a 2-dimensional structure. But I could have a list where this one has 10 elements, this one has 2, this one has 3. That wouldn't be a data frame, but it could be a list. That's fine. Matrices, data frames are almost interchangeable, except for you really don't want to do that, because a matrix is a 2-dimensional structure with rows and columns, but every element in every cell, so okay, every cell, each row and each column has to have exactly the same data type. It's like a vector down here, which means if I have street addresses, which is I have the number of the house, and then I have the street name, then my numbers become character vectors, okay, which is very bad news. So data frames are good. But the apply function came into existence. It was born well before data frames existed. And we'll do the right thing for you. If you give me a data frame, I'll turn it into a matrix. So hang on a second. We're making a matrix, making it into a data frame, and immediately making it back into a matrix, okay? And it may not be a good thing either, okay, in the sense that if they did actually have different data types, then we would actually bring them back in an uncontrolled way. And then we do it again. Why not? We're getting good at this, so let's actually do it again, okay? And then we store the answer back in the data frame, which is absolutely fine, okay? And then we very nicely clean up so that when the next time around, it'll get garbage collected. But it already would have gotten garbage collected. The next time I overwrite sim data, the value in the previous value will now become released. It doesn't get garbage collected, but R will arrange the garbage collected at the right time. Okay, so this isn't necessary. It can be good, but in this particular case, because we're going to go round again, it's not a big deal. Okay, but given that we're saving this guy and never releasing it, hey, we're in slightly schizophrenic mode of I want to clean up, but I'll just leave that big pile over here. Okay. So I'll take out this word. Okay. So far all we've done seems to be taking out characters, but it's actually changing the computational model, and in some cases is actually making it more correct. Okay. But that's fine. This is good. Now, how am I going to make it shorter? How am I going to get rid of one line?
Could you simulate the data once instead of running a for loop? Just make 16,000 and chunk it into 16 bits and get the number from there.
Okay. Anyone want to run with that? Anyone want to take that and finish and fill in the details? You do? Because I need to get, remember I'm going to need the same data structure at the end. So we need to be able to be reasonably reassured. Think about that for the moment, okay? Because that is a way we're going to do this. Okay, we're going to vectorize this to death, okay? Which is because we don't want to actually have for loops. We like to do one computation that does lots of things if possible. But so we're going to get there. So you're leaping ahead. Thank you. Okay, and I'm going to let you think about this and figure out how do we make it match to the same thing. We may actually choose not to match it to exactly the data structure I mentioned, but in the absence of any other reason, we might as well match that. But I've got rid of this line. I got rid of this line. That's 2 lines we got rid of. Okay, we simplified this line, and I said you can get rid of one other line. There's only 2 more lines, so you're going to have to guess. 50-50. Okay, but before we get to that, okay, before we get to eliminating a line, which is not just eliminating a line, it's actually eliminating an entire loop. Okay, let me just say this. You know what? I can make this code simpler to read and maintain by removing that, and this parenthesis, and this X, and that parenthesis. Do you believe me? So let me just, I can take this line of code and let's just put it in here. And I'm going to argue correctly or incorrectly that those are the same. I just can't handle that. I need to actually, okay, that these are the same thing. Which is faster? It's that one of them is that much faster than the other. So I mean, it's tiny, and so that, you know, but there is a logical component here, okay, as to why. It's just, again, I just want you to understand what it is. Okay, these are the same because I'm giving it a function, and what I didn't write down over here. So let me just actually write it down to be clear. I told you, and by the way, I scribble things down because I know what they mean. But if they're not, if my scribbling isn't quite legible, and you think it might be useful, so what do? We have lapply. We loop over a list. Okay, some list here. Okay, or some ordered vector. It can just be an ordered vector. It doesn't have to be a list. So let's actually sort of say it's an ordered collection. Okay, and I give it f as my function, and I then put in A equals 2, B equals 3. Okay, what lapply does, and you can take a look at lapply, and it's mostly, it's kind of, it loops over here, it applies f, so what it does is it makes the result here, and in this the first element of the result is going to be f applied to, this is called capital X, so x square bracket 1. Okay, with A equals 2, B equals 3. Okay, and it takes those arguments and passes them to F. These look as if these are arguments to lapply, and they are, but lapply just says, oh, those ones I'm just going to pass straight through in each call to F. And hence, what this does is sim data, it loops over sim data, it does it over the rows, and it calls the mean function each time, and it arranges to pass in na.rm equals true to every single call to mean. Okay, so this is the same thing. The other line of code did exactly the same thing. It called mean, but it actually called another function first, which was this function, which then passed the message on. Okay? So, do you believe me? You're all such trusting people. Okay, well, I don't. So how would I prove this? And by the way, do you really believe me that R is stupid enough that the apply will actually will make this into a matrix and not just do with the data frame? Or more to the point, how would I show that it really does turn that into a matrix? Same question, 2 different ways. Type of what? Of what? Of you're using the word it, which is a great word for when I don't want to say I don't want to tell you exactly because I don't know. Pronouns don't work in this game. So what is it? What I want to ask is, I could ask for the type of, but I can't ask in this function I can't ask in the function, because this function is getting the row. It's not getting the matrix. So who am I going to ask? Where? So one question I'm asking is, how do I illustrate that apply is going to actually is going to make this thing into a matrix before it starts? And then the other question I have is, how do I show that there's an extra function being called in this setup in addition to mean? And there's a reason I'm asking you this is because I want to introduce a whole brand new topic, which is, it's a debugging question. On the list of things we go over, I said debugging. We haven't gotten to debugging yet, so I've got to slide it in quickly. Okay, so I need to debug this to actually, I need some way to actually watch what's going on. And again, it's nice if you only have one computational model to debug. If you have two, you get yourself into real troubles. And that was the other thing about non-standard evaluation is when we look at the debugging call stack, there's a lot of extraneous stuff there. So it'll typically grow about 3 times as big as a regular thing because of all the extra stuff, which means it's harder to think about. But that's okay, that's fine, but it's another downside. Let's just do, so, and this is the other real trick that you really want is, I am not going to run that code to see if that's what's happening. I'm going to run a very small piece of, a small sample, a very, very small example code to see if I can test the same thing. So let's just do this. Let's take a data frame with A is equal to 1 through 2, B is equal to our norm of 2. Okay, we could, I think where you were going is we make one of them a character vector and then we sort of see it getting coerced. It's not clear who's doing that, so we'd have to be careful. Okay, so we could set that experiment up. Okay, I'm going to do it a slightly simpler way, but I like the way you're thinking, which is you got to say, how can I actually set up a computation that should essentially fail or should illustrate some other implicit coercion going on? And R is doing implicit coercion all over the place to make your life easier until it gets it wrong, until it just does it then you weren't anticipating that. Okay, so here is, we do this, let's call this Z. Okay, and now basically I'm going to say apply to a data frame, Z of 1, and I'm just going to compute I'm going to just compute, hey, look, I can even just do this. Remember I told you everything's a function call and everything's an object? This is going to call the plus function on these guys, okay? Actually, let's just do this. Let's put in 3 and 4 so you can actually guess the answer. Okay, which is apply on Z of 1 of R of plus. Okay, so this should give us back, hopefully you know what it's going to give us back. Okay, what am I doing here? What's going on? Why is that doing that? Let me just do something. What applies? Sorry, sorry, thank you. Thank you. I shouldn't have tried to be, remember what I said, don't be twice as clever as you are, because it doesn't work. Okay. So this is, okay, so this is fine, and we can, and again, just to be clear, because it drives me nuts when I see this, this is exactly what I was just talking about, get the same answer, but we'll get there too. So how do I show that how do I show that that my data frame Z is getting turned into a matrix? Or do you just believe me? And by the way, there's no benefit to believing me, because you want a trick to actually figure out what else is happening elsewhere, and this is general. So I can look at the code. Oh, I'm not going. Who wants to read the code? I mean, there's reading the manuals and then there's reading the code. Jeez Louise. No, that's fine. But what would I debug? What function? Ooh. Okay, so I can walk through that, but it may actually happen at another stage. It may actually be implicit It may not be in the apply function. And also the apply function sometimes dips into C code, in which case you're now completely out, so you can't see what's going on. It just happens. So what I'm actually going to do is something. So we can use the debugger. It's a little trickier here, but we can definitely look at it. What I could do is I could actually stop in the sum function, and then I could walk back up and see what's going on. We'll look at that in a second. Or alternatively, what I can do is I happen to know what's going on. There is going to be a call to as.matrix, which is a function. We use as dot something. We also use as parenthesis something, which is a different mechanism altogether. So if that doesn't work, I'll try the second one. But let's just do this. And that's what I want to do. Is one of the things I could do is I could do debug as.matrix. Okay? So that happens to be a function. We could look it up. But now I'm going to go back over to here. And lo and behold, it stops dead because as.matrix is actually being called. And I can then say, well, where are you being called? And it says, actually, I'm being called. These are call frames, just like we wrote in the beginning when I gave you this very long answer to non-standard evaluation. I also gave you all about how functions are called, and now we're seeing them. This is, see, I wasn't just being entirely long-winded for no good reason. Okay, this apply is our top-level call, and inside in that is calling as.matrix. And as Nistara says, if we actually just looked at the apply function, we could actually just, we could figure this out, because you could read the code, and that's great. Oh my God, this is way too long. Okay, so where's it? Well, so if the object is, if it is an object, and if DL, we all know what DL, if that's 2, then call as.matrix. Oh, okay. So I don't know if as.matrix is going to get called. It all depends on all these conditions and so forth. But here we're able to actually just see it is actually being called. Okay. So let me just do this again. Okay, and here we are, and we say where, and this is allowing us to actually watch the call stack. We're saying this is the top level, this is the entry point, this is the top level call that was being made from the R prompt or by the user. This was then called as part of that, and so forth, and you'll see these going up. Is this clear to people? Because this is, somebody was asking me recently, I got to learn Python. And it's a professor who says, I'm teaching Python and I need to learn Python. Excellent plan. Okay. And I said, you know what you really need to learn is the debugger. Okay, because that's what you're going to end up in most of the time, and you're going to be debugging students' code. So that's your first port of call. It's a useful thing. Yes?
So you type debug as that matrix. What is that telling the debugger to do? Stop when it
Stop. Anytime that function is called from here on until we undebug or turn off the debugging, it will stop dead in the debugger and say, okay, you can take over, and you get a prompt which looks like an R prompt, but it's got this attractive browse, square bracket 2 in this particular case. Okay, and then you are now in control. And now we have a little tiny, simple little language that says, hey, off we go. You can now ask it things. So I can ask it things like, where am I? And it gives me a call stack. Okay, I can say, hey, I can give it R commands, but I can also basically, I can start changing things. I can go like, but I can also do things like ls. And I am now looking inside the call frame. So I'm seeing the parameters that were defined. And I can say, well, what is X? And it says, okay, so what's the class of X? Okay, it says it's a data frame. Okay, but remember, where am I now? I can't remember. I'm in as.matrix, so it's there, and now, and that's what was passed in. So it called as.matrix, but I may have already got a matrix that would be fine if it behaves differently for that. But I can look at these things. I can do this if I want. Okay, and now I say, what's X? Okay, it's 1. Okay, and now I can just take over. So I can fix the code and continue on if I want, which is very helpful. Okay. That's the debugger. Yeah, I didn't really want the debugger. So first of all, let's capital Q for quit and get the heck out of here. Okay, give up. Or C for continue on. And next time around. Then we'll do undebug as.matrix. I say this every time I teach anything to do with R, is most people don't know about the debugging tools. There's the debug function, and then there's recover, which are very similar. okay, in some regards, but we use them slightly differently. Then there's the trace function. And how many of you know about the trace function? That's about the number I expected, which is 1, okay, out of the whole room, which is a shame because, so how many of you knew about the debug function? Okay, so still a very small proportion, which can only mean that you don't ever think you'll have another bug, okay? Or that you're smart enough that you don't need any help in debugging it. They're very cheap to learn, okay? And yet so few people learn them, and yet they save you vast amount of time. Okay, a lot of people, so what's the other most commonly used debugging command? Print, okay? I'll just print it. So I'll change my code that I don't even own because it's in as.matrix. So you don't own that code. So, okay, I won't learn the debugging tools. I'll just learn how to change the R source code. I mean, reinstall R from source. Okay, that's probably a big deal. So no, I won't do that. But you'll put print statements in your own functions, which is not good because that means you're basically saying, I'm going to print this thing because I think that's the problem. But you don't know what the problem is. You're guessing. So you're much better off if being able to say, stop here and let me ask questions. And by asking questions, I can actually have an ordered collection of questions. But I can change my mind. Oh, I didn't expect that. Maybe that's my problem. And so we start interrogating. By the way, there's another great trick, which is when you put a print statement in, so you'd say print x plus 1, or print of foo of x, where foo is some function, and then you start putting errors in your debugging code, which now means you're debugging your debugging code. Okay, and now you're going like, oh, I don't seem to be going in the right direction. I'm wasting more time. So it's useful to learn these things. The trace function is very helpful. I'm going to trace as.matrix. I'm going to call apply again. And all that does is it says, by default, all this does is it says, instead of stopping when we get a call to as.matrix, it says just print out that I'm in as.matrix. Okay? But even better, I can do anything I want. I can give any R command, and it will get run when I enter as.matrix. So I can actually call it debug. I could also say, by the way, when you get into as.matrix, evaluate the line of code that says, if the number of columns is 4 and the first value is 10.6, then I'd like you to stop. Okay, so you can do conditional debugging, okay, rather than just generic stop every single time. But in addition to which, the trace function is very powerful. You can actually say, stop in line 3 of the code, okay, under these circumstances, as opposed to debug says, I'm going to stop every time at the top. Okay, so trace is a very, very powerful function. And on Friday, I will show you actually how we can use it because I can have it evaluate any arbitrary R code. One of the things that Nastara and I were doing a while ago is when I'm trying to find out how to make code faster, I find out where all the bottlenecks are. Okay, that function seems to be taking 20% of the time. Then I ask, how often is it being called? Because if it's been called 8 billion times, speeding up one of those is going to be hard. But if it's been called once, that's a different ballgame. Well, what do? I could count them by hand, okay? But what I can also do is I can just have some code. Every time that function is called, I just increment the counter. So we can do things with trace, which is just to watch a function getting called or a particular line getting called. So that's fine. So I've shown you debug and trace. How do I show you that? How do I show you that there is an extra call when I do this? Well, we saw it. That's debug sum. Okay? Why is that not behaving itself? That's odd. That shouldn't be a problem, actually. We can untrace that, but that shouldn't. We should be able to trace and debug some, two separate things. No, the sum is happening elsewhere. Let me just do the following here, which is this is slightly odd. We're going to do this paste. Okay, that's going to be that guy. We're going to debug paste. Okay, now we're debugging paste. Okay, some is marginally interesting, but that's fine. So I can say where, and see where I am, apply, then call fun, and then call paste. Okay, now if I get out of here, okay, and now what I'm going to just do is I'm going to do exactly the same thing as I said we should be doing over here. Okay, remember, this is the same thing. It's just this argument is going to get passed in as an argument to paste. Okay, I'm in the debugger again, and now you can see there's only 2 functions being called. So again, why am I showing you this? Because it's the world's simplest illustration that there of how to use the debugger to actually verify what the heck is actually on the call stack. Okay, everyone happy? Okay. So how do I get rid of a line? I gave you the question before. Gave you lots of time to think about it. How do I get rid of one of these 2 lines? And don't tell me don't compute the standard deviation. That is a good thing because we don't use it in the next stage. That we could avoid that, but how do I get rid of it? So we said we could get rid of the function here and just call mean with na.rm equals true. We're not going to do that. We're going to define a new function. And my function, this thing goes through all the rows. And for each row, it calls this function. And then it goes through all the same rows and calls the SD function. Well, why am I going through all the rows twice? Why don't I go through the rows and compute the mean and the standard deviation simultaneously? Okay, and then it's one call. Okay, so in other words, what am I actually saying? I'm saying something like this, where I'm saying apply to sim data 1 function of x, and now I'm saying c of mean of x and sd of x, and we can put in the na.rm equals true and all that stuff. By the way, I cannot put na.rm equals true at the end of the apply. It has to go in here, because this guy doesn't take an na.rm equals true. Okay, so I can do this. Okay, I can do this. Let me just do this. I could do that. Okay, I can do this as well, though, which is I could say na.rm equals true. Okay, now that says it does take an NA optional value. Okay, I'm now defining a function. I'm not assigning it to anything, so it's kind of weird. I'm using it. I'm defining a function and then throwing it away, never to be seen again. So it's not clear I should bother putting in optional arguments when I know what I'm going to do with them. But I could define it like that. And then I could say na.rm equals na.rm. And na.rm equals na.rm. Okay, I hear giggles. This actually, if you think about this, this all makes perfect sense. That is the name of a parameter, and this is the value of an argument. Okay, with a parameter in a different function. Or I could also do this. And hopefully this is actually clear. If there's any questions, just yell. This is what I can also do.
I've done that before so many times, trying to like read someone else's code, and they're like,
So, why do I keep doing that? I knew I was going to do that. So those 3 actually are, those 3 things are, okay. So this one basically says this takes an argument, and I'm just passing it on whether it's true or false. Now then, because this guy takes na.rm, I could actually pass it in over here. This would only really make sense if this version here only really makes sense if I'm going to reuse this function in different ways. So I go my summary function is equal this. I put this into my package. I use it every day. I'm so happy with myself. I want to make it a little bit more flexible, so I add in the na.rm equals true, and then I pass it on over here. Okay, and now I'm basically going in and saying my summary. Oh, and by the way, na.rm equals false in this particular case. I override the default here, otherwise I wouldn't need to. But here, this is defined somewhere else, but it now does take this na.rm. But this version is just the same. Which version is better? Which one? This one or this one?
My summary.
My summary, why?
Then you have later on.
I have to type less later on, but I can only type less later on because it doesn't allow me to put any other arguments on. So let me just change this thing. Just this is a goofy one. It happens to be. So let's do this, which is we'll take this guy NA and we'll do a plot. Okay, so now I'm going to do something like CX equals 2. Okay, and I'm going to do plot of X. And I'm going to say CX equals CX. Okay, so now which of these would you like? So my visual summary and my visual summary here. Okay, so this is this. Now, which do you like? Bottom one? Really? Why? Because I can customize all the parameters, okay? But I don't know which parameters I'm allowed passed down. I can't. Okay, well, what about the GLM function? Do you know all the parameters for that? The GLMMM function. Okay, and it's like, oh dear, I got to look at the definition of this function to see it's calling plot, and that's where the ... dots are getting passed down to. And then I have to go look up the help for plot. And nobody likes looking up the help for plot, by the way. That's the most hideous function. Okay, it's just like, I'll take any nonsense at all. Okay, okay. It's so there's a trade-off here because. So this is much more flexible. If in our core we say, you know what, the plot function should have a new argument that's called Bob, okay? And okay, then your function here never needs to actually be changed to include that parameter, and yet the users can still pass it down and it gets used. But here, that's a problem. This is not as flexible, so okay. But the good news is I can look at the definition of this and say that's the parameters that are going to get passed down. And remember this thing about, so I go like, oh, wouldn't it be nice if I did this too? Okay. Oh yeah, that'd be great if we could add it to a plot. But I didn't do this when I first wrote my viz summary, and I'm a very conscientious person. I don't want to break all your code, so I'll add this as an optional extra, but I'll put it in the third place so that your other arguments will still be matched in the right place. What could possibly go wrong? I mentioned it earlier. The partial matching now happens after the ... so you have to be very conscious of this, that you have to spell it out add as ADD. As opposed to, close enough, AD, partial matching. So there's good and bad things, but picking up the ... So this is going to make plot do this, and then we do something like this, right? This is going to be a special plot. It's going to make the plot, and it's also going to create a PDF file, okay? So we're going to add a file name here, and we're going to say file equals, you know what I'm going to do? I'm going to actually make it this, and this is far too specific, but it's close enough. That, okay? Okay, and I'm going to do something as for sprintf of %s.pdf on dparse of this guy. Everyone with me? Okay, everyone? Okay, and I'm going to do file here, and I'm going to say width. Well, I'm going to say the width here is how many inches wide the page is and how long it is. Width equals... you know, I'll just put in ... because I don't remember what the PDFs are, what the commands are. Oh, shoot. I got 2 ... One of them is going to be specifying the width and the height and all the things for PDF. And the other one's going to be for plot. And plot does not understand width and height. And plot doesn't understand width and height. And PDF does not understand CEX. Okay, and all these things. So I can't actually split these up very easily. So If I need to pass down arbitrary things to two functions, this ... is not powerful enough. By the way, what the hell is this? I told you. And no, it's exploiting the lazy evaluation big time. So let's just do this and get an error. Okay, so this is going to be okay. So there's my function. This is how easy it is to write a function. Okay, my function, and it's going to be I'm going to plot the function. So x is equal to 1 through a is equal to 1 through 10. ABC. Okay, and I'm going to do ABC. Okay, so let's do the following. Debug of my viz summary. Okay, let's see if this works. I'm in the debugger. Okay, here are my arguments. Add file and x. Nothing has been evaluated yet because I have yet to refer to anything whatsoever. Let's take a look at x. Okay, let's actually take a look at file first. Okay, that's what we wanted, wasn't it? It used the name of the variable that we were actually plotting by default. And again, it generated the right name, abc.pdf. Now, this is not going to be, okay, but that's what it is. The substitute, remember what I was telling you, the substitute came up when I said we put this on the axis labels in a plot, because we know what the actual command was for the argument. Substitute actually goes and grabs what the expression was. Deparse turns it into a string, okay? That's all. You see this a lot, deparse substitute, which says, basically give me text that represents what the call looked like by the user, or the person who just called me. And this is fine. So this is kind of nice. It's giving me a nice default, which is that if I go back over to here and do and I could also say, no, I want to call it bob.pdf. Okay, well, that's fine. Now take a look at file. It's Bob. So the default is kind of nice here. It does the sensible thing. Not quite, because we have to be a little bit more intelligent about this, which is my viz summary of a+1. Okay, what's file? Oh, you don't want a file name like that. Okay, you really don't want a file name looking like this. And what's even worse is if this is a very long command, it actually may be broken up into two different lines, in which case I get two file names, which will be really bad news. So we have to be a little bit more careful. But this is a generally a nice little thing to do to actually help the person out, because we're saying we'll give you a file name, but if you want to change it, you can, which is a good way of writing functions. I love writing functions with 25 arguments that says you can override any of them, but you don't have to specify any of them, or only one or two. And the rest of them all actually make sense, as the defaults make sense. Everyone happy? So basically what did we say? We said we could get rid of those two lines. How do we get rid of the lists? Apply, okay? You know,
as if it was on the
we can, as David was saying, we can do them all in one big block in various different ways. But again, people's heads explode when you actually do this. So first of all, let's get it working. Okay, literally make sure we get it giving the right answer. Then let's make it smart and compare the results. Okay, so but absolutely fine. But my trouble with this was, I want to actually fix this part up first. Okay, but that means I have to run through the whole thing. So I really want to lift this block of code out. And then I want to actually have a for loop in here that calls that block of code. I need a function, okay? Everything is a function, okay? Remember I said everything's a function? Well, this isn't a function, it's a big block of code, but logically or conceptually, this should be a function because it's different from this part. This part says do this over the sample size. This says do this for a given sample size. So let's actually take this as a conceptual unit, as a task. It's a subtask, and then actually, but we're going to repeat the subtask. So let's actually go ahead and take it out as a separate entity so we can think about one thing at a time. It's hard to write code which considers everything in one go. Okay, so we divide and conquer. We break up a problem into smaller subtasks, and then we group them back together again, and then the sum of those parts should be much, much smaller. So let's So if nothing else, we can literally just take that block of code out, make it a function. So I actually wrote all this down. So rather than actually just constantly just repeat myself, so there's a whole lot of interesting things going on and on and on and on and on. What do I do? I think we, here's a function, okay? Here's a function that just takes that code, okay? Just takes that code and lifts it out, okay? It doesn't fix the truths, okay? This is verbatim, okay? So it's just lifting this out, although it does pre-allocate this. How would I make this function better? And again, if you're all familiar with this, great. This is about thinking about how to write good code, and we sort of it's obvious afterwards, but what would you actually do to make this code better? You take a look at this. Let's make it more flexible. How do we improve this code? We've talked about how we actually make it go faster and simplify it, but take that function. How do I make it more flexible or more useful? That's my sample size, I. The number of replicates, because it's hard code. Remember what I said? You see a number, a constant value, a literal, something smells wrong, okay? If nothing else, it should be a symbolic name that says this is pi, okay, or this is e, okay, that this is a well-known constant, okay? But if it's not a constant, what the heck is it doing as a constant, okay? So let's lift that out. So we can easily just do something like the following, and I hope I have it somewhere else, but we could definitely do something like the following, which is, so do sim, which is a great name, okay, which is, we could say something like n equals 1000. We add in we'll put in the verbose equals true or false, you know, and we do this. And now we say for I in 1 through n, okay? And now this is more flexible. We've immediately just made this more general. It's parameterizable. The caller can parameterize each call to it, but doesn't have to. So nothing's changed, but it's way more flexible. And again, we could take this to the nth degree. We could say, well, we could change the R beta. Anyway, is there any other way we could make this more flexible? You, sir, in the brown. How would we make this more flexible? It's exactly what you were asking earlier on. See, I do remember. Global variables. Okay, so the only way to make this function more flexible is to define alpha and beta differently and then call this function, which is entirely indirect and very hard to understand. These guys should be arguments in here. They have to be. And how would we find this? Using find globals in the code tools package. We write this function, say, what are the global variables? And it'll say alpha and beta, and we go, okay, we forgot about those. We just cut and pasted code in, so let's fix those guys now. Okay, so we'll add those in. So let's get to funds 1, okay? I still haven't got them there by funds 1 yet. I can't remember. Okay, and this is so easy to have happen, is that you cut and paste code and you forget. And it's buried down in deep in. I can't remember where we got this. Okay, there we got alpha and beta. Okay, let's skip that one for the moment. Okay, this is funds 1. Okay, somebody said lapply, and the answer is not lapply. Okay, could be lapply, but why not? Why not do this? How many of you know about the replicate function? Good, I like this. Okay, one person. There's always one person in the room who sees 2 people in the room. Okay, okay. So the replicate is almost doing the same thing. It's a little easier to understand. It says literally repeat the same thing over and over again. It's not a for loop. Typically, will actually depend on the structure on the value of this. So for j in 1 through 1,000. Where is j being used here? Here, remember we said this line wasn't important, so it's not being used. Okay, then where else is it being used? Here. Well, we want to get rid of having to put this into the list. We want to use lapply for this. Okay, so we can easily do that. We just say lapply in lapply 1 through 1,000. That's the thing I'm going to loop over, and then I give it a function, which is going to be j. Its argument is going to be j, But where's J getting used inside in here? If I remove this line, it's not getting used. So I'm doing the same thing over and over again. I'm literally repeating myself, but with a different outcome each time because of the randomness. Otherwise, this wouldn't be very useful. It's like, let's do the same thing over and over again and get the same value just to make certain. Okay, so I can avoid this. Again, I've written this down. Try to explain this thing. But this is basically, I'm saying replicate n times. Okay, what is it? I'm doing my matrix, and then I do this, which is I apply over the matrix 1, and I compute the mean and the standard deviation. So I get 2 values back for each row, and then apply does exactly the stupidest thing, okay, that you don't want it to do. It then says, I see you have a matrix that's this long, and for each row, you gave me back 2 numbers. So I'll turn the result on its side, okay, and I'll give you 2 rows and that many columns, as the same number of columns as there was number of rows in sim data, just to mess with you. So we transpose it back to actually say, do it the obvious way, please. So I will end up back with 2 columns with as many rows as there were in sim data. Everyone happy? And then I say, and don't mess with me, okay? Don't try to simplify it, because I know you will, in which case it'll do this as a list. It'll do an lapply. Replicate will do an lapply, and then try to simplify and says, hey, did you know they're all 2 columns and they all have the same number of rows? I'll put them side by side. Or I'll make them into a 3-dimensional array of I rows, 2 columns, and I'll give you 1,000 of them all stacked in 3 dimensions. You know, like, no, you won't. Okay, so I say simplify equals false. Just leave it as a list, because now we're agreeing with the code from before. Okay, everyone happy? So this one doesn't quite work because it works fine, but we didn't add alpha and beta. Okay, and I'm going to give it stupid values for alpha and beta that are legitimate, but that's fine. But now this thing allows me to loop over alpha. Oh, this is going to be useful, because I bet you, although we have the person in the room, we have several people in the room who knew why they were trying to do this. Okay, which is, remember, we have alpha and beta set once, but I suspect in most simulations you're going to have to show that this doesn't depend on those particular alpha and betas, but it actually. By the way, somebody else was asking me about this in plant sciences just a couple of days ago, like, how do I generate synthetic data to prove my point? And there's an art to it, but you sort of, but the answer is you're going to have to generate it over a whole lot of parameters to actually show that this does not, by the way, so you're going to actually simulate to show that this is a statistical property. What's the other way of doing this, by the way? This is what my colleagues then do. We prove theorems, okay? If you don't like computing, we have math, okay? Which sometimes can be easier, but sometimes not. But you might actually, there is a great thing to, how do I make this go faster? Don't do it at all, and just actually look up some theorems if you have the results. Unfortunately, they haven't proved it for the beta distribution, and they haven't necessarily proved it for this sample size. We tend to do things asymptotically, but we may be able to use some theory. We may or may not be able to use some theory, but if not, and even if we are, we tend to actually simulate stuff, and then we're going to have to loop over a bunch of different values, in which case we really need this to be a function, the whole thing to be a function, so we can at least, so we have nested functions here, and we're going to actually then expand it to be two more loops, which is a loop over alpha, a loop over beta, and then why not, let's loop over the beta distribution and the normal distribution and the exponential. Oh, good God, this is going to be huge. So, but I suspect we actually want to be able to reuse this. So, hey, we're writing packages, or we're writing software that we can actually, we're writing functions. Where do I get to next? Okay. This is what you were talking about. Here's another way of doing it. So what's different about this? This bit takes a matrix, goes over the rows and computes the same thing. It's exactly the same line of code. This one actually extends this a little bit. We didn't actually need this. I actually put in the observation number. That's just, okay, that's fine. What's the difference between this line here and funds 2? What? Nope. funds 1. Is that what it is? Yeah. What's the difference between this guy and the previous one?
Our data and here is I times 16, and the other one that's n times I times 16.
And there's a replicate. And this is so the other one had no replicate and no simplify, and it just had this line and this line, but what we had in here was capital N here. Because these are all identical. Okay, each sample is identical. We're doing 1,000 things. We're repeating this over and over again. We're generating, these are independent. Okay, so within a sample of just I rows, we're just generating them independently. But across samples, we're generating them independently. So why not generate them all in the same go? So instead of doing n operations, okay, and generating like 160 for the I is 10, instead of having 160 values and doing that 1,000 times, why not just generate 160 times 1,000 all at the same time, and then arrange them into rows of 60 at a time? And this is vectorized. Okay, we're taking advantage of the fact this doesn't always work, but when it does, it's like, oh, makes the code shorter, and it sure makes it faster, because now we don't have to do the looping, we don't have to put the answers anywhere, we just unravel the whole thing. So we're doing a huge amount of work inside and here. How would this work if we actually had different alphas and betas? So so just going back to the, yep.
So in this last solution, but just lost the sample size.
In this version, I have to remember which, I call them funds 1, 2, 3, because that's the order I did them, but I can't remember which one is which. This is for a given sample size. We still lock the sample size down, which is really helpful because, so I got the observation number in here because I didn't know what we wanted to do but what I really should have done here was actually put the sample size in here as an extra column, in which case I could have done this 1,000, I could have done this all in one go now I can repeat this for 2, 3, 4, 5, up to 24 for the sample size. But then I could stack them all on top of each other, and one of the columns would tell me what the sample size was, in which case I could have a totally different data structure, and how many lists do I have? 1. Okay, and in fact, I don't have any lists. I have a data frame that's fully self-identifying. Each row has got everything I need to be able to do the next step, and that's probably a good thing to do. One of the things I didn't show you because I said, I'll leave you to read this on your own, is basically this. At the very beginning, I say, hey, let's get rid of the inner loop, and let's just do this. So that's my do sim function. And again, I was very happy when you sent me this code. You said there's too many lists. Yes, there are, because my head hurt trying to keep the lists separate because the number of rows is growing and I can't remember which one I'm looking at. And but this breaking it down into 2 separate steps is do the simulation. This is a bad name. This should be, do simulation for a given sample size. So, okay, now it's in the word. Okay, given sample size. That would have made life a lot easier. Okay, so I'm doing that, and now I'm repeating that multiple times. Notice, by the way, this replaces the outer loop for I in 2 through 24. It's a lot easier to read, I think. And you don't see any details, but if this name was better than do sim, okay, which is better than do, okay, but but this now tells me that, okay, that's what it does. But the other great thing is I can reuse this in other places. It was stuck where it was inside the other loop. I could never reuse it. But I also couldn't test it. I couldn't actually make it reliable, and I couldn't swap it. I couldn't say, here's one version, here's another version. I actually had to go and actually copy the original code and then replace that block with something else. So by actually having small functions and then using them, calling them from other places, it gives me a lot more flexibility as to how I join them together in different ways, and I can have alternatives that are literally hot swappable. As long as they all have the same parameters, okay, they take the same inputs and give me back the same outputs, I'm in pretty good shape. Okay, everyone happy? Okay, so as I say, I've written down a bunch of stuff that actually talks through what I talked through quickly. adds in a little bit more explanation, I hope, okay? So, but if you have any questions, please yell. So, step 2. That's my argument to step 2, okay? Okay, which is close. And this actually brings up a bunch of fun stuff. This is why I loved your example. It's like, oh yes, I'm going to be able to hit so many nice things, okay? Here is step 2, okay? And again, I have not fully shifted over to a different data structure. I was trying to actually keep close to the original, but I did actually, if you take a look at the first one, we ended up with a list, and each list had 1,000 elements, each of which was a data frame. I got rid of the data frame and got a matrix, but there was the same number of columns and rows, so it didn't really bother me. Data frames are unnecessarily cumbersome. I actually added an argument that says, you know, this is really goofy. Why do I have a list of 1,000 2-column matrices when I really should stack them all together because they're all for the same size? So I could do a do.call rbind on that list. Remember the do.call that we talked about? So it comes back a lot, okay? And I said, so I could have done that. I could have actually changed my outer loop, the lapply of 2 through 24. I could have added that, but I said, why don't I just add it as an argument to or as a parameter to my doSym function? Do you want me to leave it as a list, or do you want me to bind them all together into a matrix for you? That's just an optional argument, but again, it adds flexibility. Now, how do we get this? How do we get rid of this? Okay, this is fun. Here's a for loop, here's a for loop. It's the same code. By the way, the way you should have written this for speed is you're doing a loop over i's and then a loop over j's, and then you're doing the loop over the i's, the 2 through 24, and then a loop over the 1,000, which is essentially the same loop. So you should have mixed them all together, like into one massive middle point. Oh, that's even worse. Now we're combining things. We said we wanted to separate them so we could call them independently. Okay, and now we're saying make the middle part, the inner loop, do even more, which means we're going to actually have to test that code all in one go. Okay, so no, we don't actually want to glue them all together. For speed, we might, but for sanity, we don't. Okay, so and later on, we could actually even figure out how to make this really flexible by actually doing both inside the loop, inside the same loop for speed. But let's only worry about speed when we got the code running. And we actually say we need to spend time making it faster. What's going on here, by the way? Remember what I said to you? We first of all loop over the 2 through 24 elements, okay? The sample size. Then we go through and we take each of those elements. So this is like an lapply. We could easily do an lapply over this. But what are we doing here? It's the 1 through the length. We allocate the results. We don't pre-allocate them. So we should have said vector of list with this number of things. We have a for loop, and then we shove the answer into something, and this makes me very anxious because why does it make me very anxious when I see that? What 2 things make me anxious about that line? It's one concept, two words, not a word, 1 character, 1 word. I'll be more specific, it's not the equal sign. Okay, this is a list. That is not the way you talk to a list. Okay, that's the way you talk to a vector. Single square bracket means give me that element. Double square bracket says give me the element in the list. Okay, and I need the double square bracket. I don't know what's going on here. I have to think. And by the way, as I say, I'm not trying to pat myself, but I've been doing this for 25 years. If I don't know this language by now and I have to think, it ain't good. Okay, this is bad news. So this should be double square bracket. But hang on a second, it's the same problem we're having. Why am I coding where to put the answer when this lapply guy or sapply or vapply, which all do these things, will actually pre-allocate the answer and just fill in the things in order. Just let it do it, okay? There are times when we can't, when the for loop actually depends on the previous iteration, and I actually have to know what happened, and I have to do one first before I do the next. But in this case, no, I'm just doing the same thing to all the elements, so let's just use one of the applies. So I can do an apply here, and I can do an apply here. This here is saying skip over so this is j modulo 2, which, so I divide j, so j is 3, I divide by 2, get 1 as a remainder, which means yes, turn it on. Okay, now, is the mean or the SD the first one? And what do we do with the last one? Is that an odd or an even number? It's, okay, it's hard, okay? I like to say, hey, go find me all the columns that are the means, okay? And just subset this guy, which is what we're doing, not with j one at a time, but with all of the j's, like 1, 3, 5, 7, 9, okay? So I do that by saying, give me the sequence starting at 1, with by equals 2 to get to 3 to 5. And then how many do I need? Well, I need the number of columns divided by 2. Thank you very much. We're done. Okay? So that's fine. I can do that if I wanted to, or I could actually also say, remember, this is one of those wacky things, because we used this hideous abomination up here, this is a hideous abomination that R should not do this. As data frame, they all look the same. Let me just concatenate them sideways. Okay, this is bizarre, but we now have a very, very long number of columns. We have 2,000 columns of SDs and means, and because R does that, it says, oh, I better change the names to be mean. Okay, that's good. SD, good. Then mean 1, then mean 2, and then 3 up to mean 999. So I think there's one missing when I go to do these calculations where I'm off by 1. Did I not get the last guy? No, it's R. Didn't put the 1 on the first guy because it decided, oh, jeez. Okay, so we're fighting here. Okay, so that's fine. Okay, so we can do an apply. Hopefully, and again, I've written the code to do this. So if you're there are details there. If you, by the way, I hope this works. This is close enough, but we can fix it easily. But so first of all, I don't have to. So, but we're doing two things here. We're computing this. By the way, this is something else people. Remember, I said there's a principle called dry. Don't repeat yourself. We are repeating ourselves here. We're doing a stupid, annoying, hideous calculation, and we're not only are we doing it, we're doing it twice. So if I make a mistake, I'm making a mistake in 2 places, okay? And then I'll probably forget to update this. What we really want to do in this particular case is very simple, and this is, very few languages do this. We can say x is equal to if our uniform is 1 is greater than 0.5, okay? Any condition here, we'll say, give me 10, else give me 5. Okay, this is a very weird thing. Most programming language will say, if the condition, then some expression, and we'd say x equals 10, else x equals 5. But R, because everything's a function call, including if, just says, give me the answer, and then I'll do the regular thing of assigning the result to a variable. So you can assign the value of an if call to a variable, which means I can replace these 2 lines with just this thing is equal to, well, if this condition is true, then it's NA. Otherwise, it's this thing. And therefore, I only have one calculation as to where to put the answer. But I don't want that anyway. Okay, again, this is written down if you want to look through it. But the key thing is I can actually take, here we're assigning in 2 different places to the same thing. I can put it on the left-hand side of the if statement. That means I'm not repeating myself. That's good. But in fact, actually, what's happening here is, as it says, this is very nicely documented code. It says sometimes an error with, throw in an error sometimes with smaller n. Okay, and we can't remember exactly when. Don't ever do that. Lock the error message down when you get it. Just grab the error message, try to debug and go like, okay, I'm not going to deal with it now, but at least we'll remember why. Okay, because then it becomes impossible to remember what the bug was. Okay, and we could potentially deal with this in a different way, more defensively. But this is good. But this is fine. So, but what it's basically doing is the following. If this did, so I mean, if you do something like, I suspect, if we do something like a t-test on 1.3, just so I won't give it an actual value, we just say, hey, there we go. We'll say mu is equal to 0.4. Okay, it should say there's not enough x observations because again, you can't compute the standard deviation. Okay, so it goes, that's stupid, okay? So I suspect that's what, and that's why they started with 2 rather than 1. 1 through 24 is the sample size. We weren't going anywhere, that's great. So, but this is good. How many of you have seen and used the try function? Okay, it's a great way of saying, you know what, I don't mind if I get an error, just keep going. Okay, just keep going, I'll deal with the fallout later. Okay, and it typically is important when you're saying, I got 1,000 things to do, I don't mind if some of them fail, I'll figure it out afterwards. Maybe I don't care about them, or maybe I'll be able to fix them up later on. But what this does is, so the try function says, do this command, and if you fail, give me back the error message. But if you don't fail, give me back the actual answer. So then we say, hey, did you fail? And then we say, well, if you failed, set output to be NA, and then we use output down here. But otherwise, output will actually be something, the result of the t-test, which is a list, and that contains the p-value that we want. How do I get all of these lines to be much simpler? First of all, I'm going to do this. I'm going to change results to be a list. We're kind of going to do the lapply thing, but let's not worry about that quite yet, because it requires extra tiny little trick. I want to pre-allocate this. Okay, results. I'm going to do this over, results is going to be over, it's going to be 1,000 long, okay? Exactly where and how I do this, I wrote it down, okay? But rather than say, give me a list with 1,000 empty elements, I'm going to say, hey, give me a vector, because these are actually p-values, so I don't want a list. I want a numeric vector of values between 0 and 1, I hope, okay? And by the way, start them all off as being NAs. And then I don't have to worry about this nonsense. If I don't get a legitimate answer, I don't set it, okay? I just leave the NA there. So that's going to that's going to simplify my code. Basically, if this is not true, then then I succeeded. Oh God, double negatives here, okay? So, it's, in which case I can drop this line of code out and I can just say, give me the p-value. Or actually, I could even just say, give me the p-value here, $p-value. And then I can just say it's the value of output, and that life is good. Everyone with me? If you have any questions, by the way, yell. But it's written down, so if you're willing to trust me. Okay, so I can get rid of, I can say if this, and so I don't even have to do this. I can change this condition just to be this condition, and just put this line in here. If I just negate this, so I say if it isn't an error, then do this bit, okay? And then all the rest of it, and then this bit goes away. I don't need to set output. And if I take, you could argue, well, hang on a second, if it was an error, you're not seeing the error message. Well, we turned off the error message, so let's just turn it back on again, okay? And then I don't have to actually issue the error message. So I can collapse a lot of this down. I got rid of this guy by actually only looping over a subset of the thing. And now, can I do better? Apparently I can, because why would I ask otherwise? How many of you have seen this guy? Two people in the room, that's fine, because otherwise I'd be very depressed if I was wasting all of your time, okay? And if you think that, oh, well, I don't need this stuff, I don't write software. Have you ever done a simulation? Okay, have you ever written stuff that loops over 100 files? Have you ever looped over and scraped websites where you need to recover from anything, including the web server dying, okay, and nothing to do with your code? There's lots of times when you actually need to handle errors. There's lots of times when we actually need to write code that repeats over different values, be it simulations, different files, different samples, whatever it is. This try-catch is slightly different from try. What we actually do is we say, yeah, go ahead, do the same computation, which says compute this thing. Okay, this is exactly the same code as I just showed you inside those two loops, or sorry, inside the inner loop. Okay, it's doing the same thing, but this says, try this, but if you get an error, I'd like you to execute or to call this function. And all that function does is says, I'll give you an alternate value for that computation. It's just NA. Okay, and I'm done. I could go off and I could, call a friend or something like that in that function, and to get a different answer. I could put a beep in there. lots of beeps. Yeah. So, but I can handle this error in any way I want, and I can even do better than this. I can actually say it's a particular type of error, I can handle different types of errors differently. So saying this is a network error, this is not a number error, this is not enough observations in a t-test error, and then I can behave differently. Okay. Somebody had that. You had your hand up.
Is it possible to, in the previous function, attach names to those columns, but miss the mean? Like I want the columns named mean.
So the simplest way to do that is, yes, because R makes this 2000 wide thing, the names are actually mean.1.2.3, okay, and so forth. So you could actually just say grep for the word mean in the names, and that would identify true, or grep-l, and that would identify trues and falses, or it would actually give you back 1, 3, 4, 5, and so forth, okay? In this case, I'm actually just, which one is better, I don't know. Here I'm actually just saying, do it this way. But if they did come back randomly, if you will, which I don't know why they would, but if there was something, if there was some other identifying feature, yeah, we would just we would come up with a different mechanism to identify the columns that we wanted. Yeah, and whether that's by saying, look at the names and look for the word mean, or look for the word SD, or whatever it is, that will be, or else we happen to know it's 1, 3, 5, or whatever it is, whichever is most appropriate. That's problem specific, I think. Okay, any questions? So you get your money, so that you get your money's worth. Here is somebody came to me with a problem like this. So here's actually, so this was written in a class of mine over 10 years ago. And somebody sent me an email saying, can you help with this code? And I'm going like, 10 years ago? This is nuts. This is written by a student who, an undergraduate student who took a graduate class with me, and then went off and did her PhD down in Berkeley and stuff like that. And I'm sure she'd be mortified if she knew I was showing her this code from a very long time ago. So this is what I got. Okay. They read in a file. So remember the data business, and I so said, excuse me, you gotta send me the data too, because I can't get past line 1 and I have no idea what it looks like. So they sent me that. They do this, and again, this is hard coded, so it's only one file. It can only handle one file. This is actually a graphical user interface. Okay, a very old graphical user interface. It's got buttons and plots inside windows and stuff, which is so much nicer. Okay, so if you can run this, if you can run it on Tickle, if you have Tickle TK installed on your machine, which comes with R, but if it's got those libraries enabled, you could actually run this code. I believe that you just source this, and then you call this function, psm creator.open, paren, and good things will happen. Buttons will come up. You click on the button, and you say, load this other file, and then you click on another one and say, load this other file, and you have to know what the sequence is, and I have no idea what to do. Okay, and this is annoying, because it's not like a script where I just run it and get an error. This is, I actually have to know how to use this graphical interface. And I have to do that because even if I did know the script, here again, if you don't understand this code, that's fine, okay? It says, this function, get pos file, okay? Get the positive sequences, okay? It says, it's a function that takes no arguments, no inputs. And it then goes off to the graphical interface, because it gets called when somebody clicks a button. Actually, it doesn't. Does it do that? It says, go choose a file. Get the value of that off of the graphical interface, okay? And then it says, well, okay, so if that thing is empty, so if you didn't pick a file, it says no file was selected. Otherwise, it says, ready to go. So let's go, okay? So you can see all this stuff. So I'm showing you this. I want you to be thinking, what could we do differently? Now, input negative sequences. Click on a file. If you didn't select one, we'll tell you that no file was selected. Otherwise, we're ready to go, and we read the file, and we do all of this stuff. Do you see any similarities? It's almost the same, except we have different variable names. And we then assign all of these things over here, which is good and bad. And so, you know, there's certain things you actually do have to do, but that we may not want to actually do it this way. But all of this work, we have these numbers here, which is, again, these are constant values, which means something smells bad. Where do those numbers come from? This assumes that we're reading in genetic sequences that have exactly 11 characters uniformly throughout this thing, no more, no less, okay? And it turns out that if you don't have 11 characters, then you better put a period in to actually say, we don't know what the value is for this element in the sequence, and so forth. So, there's a variety of problems here that we could make this more flexible. We could actually just compute the number of characters in each line and then just check that they are all the same, or we could expand them out to actually make sure they all have the same as the maximum number of characters. Okay, that's something we may want to choose, but we could write a function that helps us do that and adds these checks. We could have this, we could actually then have one function that is able to read the positives and the negatives, because it's almost like they're exactly the same structure. But most importantly for me is, I need this code outside of this function. It's got no business here. We're doing two things. I'm choosing a file and I'm reading the file. Why am I doing those in two separate stages? Because if I had get the name of the file and then now call a function that says, here's the name of the file, I could quite happily come in without the graphical interface and say, here's the name of the file, can you read it for me? Okay, which is a totally different ballgame. Okay, so if you're writing a Shiny app or something like that, the modern equivalent of this is hilariously old, okay? You actually want to keep the code that is doing the data computation separate from the code that is doing the graphical user interface components. If for no other reason, for two reasons, so that you can reuse it in other places, but also so you can test it, okay, independently. It's remarkable. We were making slight changes to it to actually see what was wrong and trying to debug it. And every time we made one change, we had to go through, okay, fire up the graphical interface, click 5 buttons to actually get back to the state that we were in, whereas I could have easily just saved where I was and then just redefined a function and continued on from where I was going. So having small functions that are that you can call from different starting points is really, really critical. That's why we want really small functions, okay, that do very specific things that you can then combine them in different ways and have different entry points. So if you actually go through this, I actually wrote down some comments. So in here, there's some comments as to what could and what you could do, what you could do better and so forth. The reason somebody asked me about this was there was 2 bugs in the code. Okay, so we had to debug it. This was part of the game. Let me just show you this. Again, we'll finish up very soon, which is this, I believe. This was one of the bugs. What's wrong with that? I'll give you a hint. It's not on the left-hand side, it's on the right-hand side. So this was a funny one. It was like, oh, it was kind of weird. So it took us a couple of minutes just to figure out what was going on. It's not a very complicated bug. It took a long time to actually get to the point I could run it. To give you a little bit of background while you're looking at this and going, and something will come to mind, it was even more fun. I sort of said, hang on a second, the code you sent me doesn't actually source. So how are you running it? And they said, I don't know. And we figured out that he had a version saved in his R data from RStudio. When he quit out of it, it saved it. And when he started back up again, it was running, but it wasn't the same as the code was here. And we do not have any idea what difference there was. But it's like, oh, this is ugly. This is really, really ugly. So we were not working off the same code. So this is bad news. So what's the problem here? Or what's a simpler way of writing this? What we're basically doing is you have read a bunch of lines from a file, and you basically want to say, if any of the empty lines need to get out of here. We just want to drop the empty lines, like the last line, which has nothing in it. Or maybe there's just empty lines. So this is more verbose, but it's also wrong, okay? Because what we really want to say is positive.hold does not equal quote, quote, okay? That's much easier, okay? This says, get all the ones that do and then drop them, which is double negative. Like, it's just harder to understand. But this is very bad when there's no blank lines. Because now, which of this will give me back an empty thing? And if I drop with integer being empty, so I get an empty integer vector and I say drop them, it drops them all, everything. Okay, so this is a degenerate case, a pathological case where you're on the boundary condition, which is use negative indexing to drop things, but I'm giving you nothing. So what do you drop? Everything. Okay, so this is one of those wacky things where it's much easier just to say this not equals quote quote, and there's no degenerate case. Okay, it just does exactly the right thing. So this is good. Then there was another bug in here which I just showed you how to deal with this. Okay, and this is one of the reasons I was going to show you this. Until Michaela sent me hers yesterday, and I hit almost all the same topics. But this was one of those fun things. And again, this is 10-year-old code. Nobody did anything wrong here. But down here, I can't remember where it is. So we do plot. It's this call here, caused grief. And what it did actually was says, okay, what these are, how many? What it's doing, as you can tell, is it's actually plotting ROC, receiver operating characteristics curves, okay? So it's actually showing these curves. There's a package that does this, so that this is a well-written piece of code that uses a package that does the right thing and reuses code. So this is good. As I say, this code was written 10 years ago. This has a dependency on the ROC package, so you install the ROC package not from 10 years ago, but from now. Okay, so you can hopefully hint this. I'm hinting at where this is going. It ain't the same code, okay? But it's darn close, which is pretty impressive that you can pick up a package that's 10 years older and it still works and does the right thing. But the error message that we were getting was plot this, blah, 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 and it says type there's two arguments named type, and that's not legit. You can't have the same argument name. You can't have two arguments with exactly the same names because we can't match them like we talked about at the beginning of the class, our session today. So what was the problem? So this goes back to, remember those functions I defined with dot, dot, dot in them? Okay? So you can shovel anything down, and the ROC thing picks up what you give it and shovels it down to plot as well. The trouble was, when this code was written, the plot function from the ROC package didn't specify type equals L. 10 years later, it does, but this code wasn't matching correctly. But it became very odd. So who's actually passing this down? It's all through the dot, dot, dot. The debugger just shows you exactly what's going on here. You walk in, you go, uh-oh. You can walk up and down the call frames and go like, what code is, oh, that's fair enough. I see what's going on. And you go, okay, let's just drop this guy out and everything behaves itself perfectly well. Okay, but one of the points about this is, so it's good to debug these things, but it's really, really important not to repeat yourself and to actually have code that isn't mixed in doing two things. One, in this particular case, is choose the name of a file and now read the entire file and format the data is just crazy. Those two have to be two separate things so that you can reuse and retest that code completely outside of